Good morning, everyone. I think we're about to get started. So I'm Andreas Mueller. This is Kastner. Welcome to the Machine Learning with Scikit and tutorial. So this is going to give you a basic tour of machine learning and how to do it in Python with Scikit-learn. So this is a two-part tutorial. There will be 4 hours in the morning that introduces concepts and the general API of Scikit-learn and general things about machine learning. In the afternoon, there will be a bit more advanced topics. So we have plenty of time. So if you have questions, please ask questions. If you have problems following along, let us know. If we are going too fast, let us know. Yeah, I think that's about it.
I think that's it.
All right.
All right, so we're off. We have a number of notebooks to cover this morning. It's bright and early. People are still kind of filtering in a little bit. Hope you have your coffee with you. The first kind of chunk we're going to go through. First off, let's make sure that everyone has the tutorial content. Does anybody not have the tutorial content on their on their laptops right now? It's like notebooks. There was a fetch data script that we wanted to run beforehand. Okay. Okay. So as long as you got a buddy to help you out, everything's good. Yeah. So as long as only a few people are fetching the data, we're fine. If everyone fetches the data at the same time, the conference Wi-Fi melts and somebody screams down the hall. So good. So if we have that bit.
So when we're 2 people, so you can also raise the hand if you have problems. So the other person can run up to you and help you out while the other person is presenting.
So Andy has just volunteered himself for the next hour, and there you go. All right, so if everyone has the notebooks and the tutorial content, we'll leave the link here on the whiteboard in case anyone forgets or comes in later. The first chunk will basically cover what is machine learning, how do we represent the data, how do we plot it effectively, what tools do we use that underlie scikit-learn? So that's stuff like SciPy, NumPy, Matplotlib, kind of some general stuff. Then we'll present one way to represent data for machine learning. It's the most common way. It's the one we like the most in scikit-learn, but I'm sure someone out there will disagree and say you should use columns, and we'll cover that in a minute. After that, we'll cover some of the really fundamental stuff, training and testing, what that means, why it matters, and why you can fool yourself into thinking you're doing better than you actually are. Then we'll cover classification, regression, kind of the core scikit-learn, and then after that will be a bunch of methods and applications, and that'll finish out the morning. And at some point in here is a break as well, around 9:45, 10 o'clock. It's supposed to be snacks. We want to make sure you guys can get to the snacks because we want you to be happy. All right, so without any further ado, I'll start with an introduction to machine learning in Python. So what is machine learning exactly? When people sit down or come in front of you and give a talk and say, we want to do machine learning, we think machine learning is really important to making our lives and societies and businesses run better and more efficient, what do we mean? Fundamentally, we mean that we want to collect a bunch of data and we want to extract knowledge from that data. We want to, in some cases, we have very little data. Cases like large manufacturing, you have very, very little data and you need experts to kind of take their PhDs, put it into math, and help you make a decision. In other cases, you have stuff like images and video and audio where there's huge, huge, huge volumes of it just laying around. In that case, you might want to do something a little more free-form and just extract information from the content itself. So machine learning is like really broad, and it covers everything from what most people would call computational statistics, which is another tutorial this morning, all the way up to deep learning, which is a recent kind of re-innovation of the field. So it's pretty broad, and they're quite different at either end of the spectrum. And I would say scikit-learn kind of sits in the middle. We try our best to give you as many tools as possible up front and let you work with the data that you have and make automated decisions in the simplest way possible. Put your knowledge in, use the black box algorithms in a simple, easy-to-use API, which we'll cover, and from there, it looks kind of easy, and that's the point. By the time you're done with this tutorial, you should be very, very comfortable with Scikit-learn. So, with all that said, I've basically covered most of the text that's here. We want to make decisions automatically from data, usually without the user specifying explicit rules on exactly how the decision is made. We want to use the data to inform our decision. We want to use our knowledge to inform the decision, but we don't want to hand code it. We talk about the classic example is a spam filter. Everyone uses email these days, or I hope so if you're in this room. We get lots and lots and lots of email. Anymore, most of it's spam, and a little bit is not. So we have clear labels of this is spam, this is not spam for a huge variety of users. But for any particular person, what they consider spam and what you consider spam may be a little different. So there's an element of generality. This is broadly what everyone thinks is spam, and then there's also specific, user-specific spam. So you want to take all of that knowledge, put it into what we call an estimator, or in this case, a classifier, that basically all it says is, I got an email, this is the content, this is the text. Spam or not spam. Different methods will give you more or less information on the side. If it's a method that can be interpreted probabilistically, it might tell you something like there's a 0.8 probability this is spam and a 0.2 probability it's not. And then depending on who you are, you might say, well, I like reading a lot of trash in my email, so set my threshold at 0.8 and give me that stuff. Other people might say, I want borderline guarantees that I'm not seeing spam, and then you have higher rejection. And we'll talk about all of this in more detail in the following notebooks. But at a high level, this is kind of the type of problem we're trying to solve with machine learning. We have this huge volume of data, and we have to automate. We have to find a way to make a decision. So I also talked about specific users and general users. That kind of ties into the concept of generalization. When we build a classifier, it's not particularly useful if the only data it works on is the data we already received. We want our classifier to work on new, unseen data. That has a fundamental limitation of the fact that people can't see into the future. We can't have data we have not collected. We cannot have data that hasn't come into the system yet. So we have methods and ways to approximate this by basically holding part of our data separate and saying, well, pretend like I haven't seen this yet, train my classifier on this piece, bring this new data in and see how I perform. We'll talk about that a little more. That's the idea of training and testing. Very, very, very important. I would argue more fundamental than any of the algorithms, any of the other things. Methodology is crucial, because if you do not have training and testing splits, what happens? You train on all of your data. You believe that you're doing very well. You take your classifier and you deploy it to AWS and you tell your boss, we're doing amazing. And then new data comes in and nothing works. Very, very bad situation. So if there's one thing I can get across in my morning discussion, it's that methodology, training, and testing, very, very important. So let's look at a diagram that kind of shows this. And it doesn't quite fit on the screen, but we'll scroll through two halves. So here is what we call training data and training labels. So for classification, the labels are the thing that tell you what the data represents. Is it spam? Is it not spam? There are other methods that don't need labels called unsupervised methods, but we'll talk about that later. And these labels could be something like this is spam, this is not spam, or in the case of something we call regression, these could be floating point values like you have a sine wave and you want to predict the next values in a sine wave. So labels is very, very, very general, but broadly we have to have something to tell us whether we're right or not. So the training data and the training labels come into the model, and the model could be anything that's in scikit-learn that's used for either classification or regression, depending on the type of problem you have. It takes those and figures out some way, through some mathematical process, how to take the input training data and map it to the training labels. You learn some function that maps data to labels. And if you generalize well, if you work on new data, then in theory, you should be able to take that test data, put it into the model, get a prediction, and it should match what the test labels say. And if you're doing really, really, really well, you might get close to a perfect score. And in that case, in the case of like very, very, very good scores, you should maybe be a little suspicious in general. So the most important thing is this training and testing split. And I cannot emphasize this enough. It seems like a very, very simple thing, but every year there are multiple papers in the field that have to be retracted because this fundamental principle has been violated in some obvious or subtle way. Be very, very, very clear that your training data and your testing data are not the same. They are different. And that the training and testing data should approximately represent what you expect to see out in the field in the real world. So now we'll start talking about how the data is represented. And there's a larger notebook in the next section, but at a high level, you can think of the data as an array of numbers. In scikit-learn, we exclusively deal with a 2D array of numbers. There are other ways to represent data as a 2D or a 3D array. Typically, we like to deal with 2D arrays. It's a very specific type of problem. Normally, when you inject a third axis, that's time, and that's a very specific type of algorithm. Scikit-learn used to have something called an HMM, which was focused on kind of a 3D array of numbers or a list of 2D arrays. And that's often its own package. So if you want to deal with kind of time series type data, there are tools for it. Scikit-learn has kind of pruned the scope and said we're going to focus on algorithms that work well with a 2D array of input data. So now we want to talk about what that array of numbers means. Well, we'll talk about that a lot more with better graphics in the next section. So let's gloss over that and talk more about broadly the two types of machine learning that people care the most about, classification and regression. So I mentioned that in the spam, no spam example, we have an array of data and some labels that say spam or not spam. This is classification. We have some set of labels and we're taking input data and mapping it to one of this set of labels. Spam, not spam. More complicated examples are identifying people in the photo. Recommendations is kind of a mix of classification and regression. Inferring salary, that's more of a regression case. You're predicting a numerical value. Something like predicting a time series, say you're in the stock market, you care quite a lot about predicting the upcoming numbers in a time series. That's going to be regression. So those are kind of the two primary supervised tasks in machine learning, classification and regression. There's kind of a spectrum in between there, but for this tutorial, we won't get into it too much. Broadly, we have some set of data that is labeled, hopefully a lot of it. So that's another important point. Data is king in machine learning. The more data you have, and especially the more labeled data you have, the better off you are. And we'll discuss the fine points of this later, but typically when someone says, do you want more data? You say yes. Please give me the data. Even if it's messy, even if it's noisy, even if it's whatever. You can always not use it, but collecting data is expensive. Sometimes very, very expensive. You can imagine you're in a world where there is no spam labels, and you just have everyone's Gmail account, and no one has ever classified spam or not spam before. You have to hire someone to sit down and read all of these emails and figure out what is spam and what is not spam. And at some point, their brain will fry and they will scream and they will say, no more advertisements, no more whatever. It's expensive. You have to pay someone to do these labels typically. There's ways to bootstrap around it and use other algorithms, but nothing really compares to having a person sit down and generate your labels. So you want more data if you can get it. If you can't, well, okay, there's ways to make do. Once again, there's a distinction between training and testing data. We'll go over this again and again and again because it's very important. So there's also a number of techniques for something called unsupervised learning. What this means is you can take data and learn some model that, given data, can predict data. So there's a number of algorithms to do this. Clustering falls into this. Density estimation falls into this. Dimensionality reduction falls into this. If you've heard of something called an autoencoder, that also falls into this. Basically, you don't need labels, and you're trying to learn something fundamental about the data from the data itself. This is kind of, when it works, it's incredible. It's kind of the holy grail of machine learning to actually do unsupervised learning very, very well. Unfortunately, typically, it's much, much harder to learn something in an unsupervised manner than to use the labels to say, hey, this is spam, this is not spam. Imagine giving a whole volume of emails, millions and millions and millions, and just saying, learn what a general email looks like, just in general. Then based on that, I have a model that can probably generate emails. Then figure out how to say, after you generate, which one's spam and not spam. Generating emails is much, much, much harder than reading them. So this is kind of one of the downsides of unsupervised learning, is typically the task it's trying to solve is much harder than classification and regression from a mathematical perspective. So some examples of unsupervised learning are determining which features summarize the information in an image or an observation. One really cool example is blind source separation. Imagine we're in this room and 20 people are talking and someone records it and they say, I want to separate each of those 20 people's voices out individually. It's a hard problem, but when you can do it, it's very interesting. It's also unsupervised. Isolating objects, not based on their label, but based on the fact that they're moving differently than other things in the image. Basically figuring out that different things move at different rates and separating them in that way. Finding the topics in news articles is one of the most common and useful, I think, methods of unsupervised learning, and people use it a lot, and I believe we do an example of it at the end of the day this afternoon. Given images, figure out what images are similar, what images are different. Based on that similarity, you can do things like search and relevance and things like this. So, broadly, supervised learning, unsupervised learning. Most people are going to be focused on supervised learning, but unsupervised learning is there, and it's also very useful for something we'll call preprocessing, and we'll go into it more in the following notebooks. So, all that said, now we can move on to 1.2, which is IPython, NumPy, and Matplotlib refresher. And I won't go into too much detail about this, but I guess before I do that, does anyone have any questions, any comments? Need a break? Are we still okay? Training and testing data, we get it. Kyle, stop talking so much. On to 1.2. Yeah.
In the beginning, you said that the Scikit package was 2D data, but there was a time that it handled 3D data, and that third axis was time.
Yes.
But you can have 2D data with time as a variable. You only have one up there.
Yeah, so the question was about 2D and 3D representations of data and incorporating time into a 2D representation. It's absolutely correct. You can represent time as a variable in a two-dimensional array, no problem. You can even have features that represent statistics over time, things like moving means, moving averages, so on and so forth. But there are also algorithms that specifically have to have time encoded as its own axis independently, and they make very specific probabilistic assumptions about how each element in the sequence is related to each other. I won't talk about it too much, but kind of when you get into that domain, you get into some stuff that Andy and I study, which is called structured prediction, and there's a whole mess of problems that are related to that. And so Scikit-learn at some point in 015 said that HMMs are kind of their own beast, they're kind of unique. Let's break them off and put them in their own package. But you can absolutely handle time series in a 2D array, no problem. All right, so NumPy, Matplotlib refresher. First off, everyone has IPython notebook up and running, no problems. I didn't hear any major issues. So if you haven't used the notebook, it's pretty straightforward. You can go to your terminal. Let me see if I can actually do that here without everything going away. You can simply go in your terminal, type IPython notebook in the directory where all of these notebooks are, and that will start the notebook app. That should pop up in your browser. And if not, you can always go to localhost :8888 in Firefox, and it will pull up this nice display that looks like this. And you go down, click on the one you want to look at, in this case 1.2. It'll pop up in a new tab, and there you go. You're in the IPython notebook. Really great for presenting, really great for exploration, and really, really nice tool that's come a long way in the last few years. So you can run a cell by pressing Shift and Enter. You can get help by pressing Shift and Tab. You can also, kind of like IPython in the shell, if you've used it, type something, put a question mark, and pull up the doc strings and see the help and all that kind of stuff. There's also like a number of really nice tricks, and you'll notice it used to be called IPython Notebook. Now it's called Jupyter. There's a reason for that. It's because it supports a lot more than just Python. A lot of really interesting stuff goes on in IPython Notebook, and I think there's a number of talks and tutorials about all the stuff you can really do in Jupyter Notebook. So if you're interested in that aspect of stuff, definitely go check it out. So now, NumPy arrays. NumPy arrays are one of the key parts of doing any scientific computation in Python. Really incredible, really important. Basically, you can think of NumPy arrays as an ND generalization of your classic matrix. So if you've ever written C and C++ code, you've probably gotten to the point where you have for I, for J, for K in matrix, loop through every element and do something. NumPy kind of wraps these kinds of computations in an intelligent way and lets you operate on big blocks of numbers in a vectorized fashion. So if you've ever used MATLAB, it's very similar conceptually to what MATLAB lets you do. Take a big matrix, add another big matrix, take a big matrix, multiply with another big matrix. NumPy extends these a lot further. Once you get past 2D, it starts to become a tensor, so NumPy supports that kind of stuff by default. It's kind of a big deal, and it's one of the reasons we're all here. So without further ado, let's just look at a NumPy array and see what's going on there. So the first thing, we import NumPy as MP. That's kind of a convention, but if you like using NumPy, go for it. We generate random numbers to fill an array. It says this is a 3x5 array, kind of specified here. We print it out, we see that it has 3 rows, 5 columns. That's our 3x5. You can access single elements, so if you want to get the element that's in the top left corner, you can do that. You can also get a whole row by saying x of 1. It's zero based, by the way. If you're used to MATLAB, there's going to be this time of, is it 1 indexed, is it 0 indexed? It's 0 indexed. It makes math better. Biased opinion, 0 indexed is superior, but you know, everyone has their own argument. Get a row. In this case, we'll select this whole row. Get a column. In this case, we select the first column right here. Yeah. So we can see that we can put a 2D array into memory and access the elements kind of willy-nilly. So this is great. We can also transpose it. So say we wanted it to be 5 by 3 instead of 3 by 5, we didn't want the numbers to change, we can just look at X transpose, X dot T in this case. It's like the tilde from MATLAB, or dot tilde. There's some weirdness with complex numbers, but we deal with real numbers typically for scikit-learn, so don't worry about that. You can also turn row vectors into column vectors here by adding the new axis notation, or sometimes you'll see colon, comma, none. That's the same thing. Basically, you're just saying, take all these elements, and I want it to be rows with a single column. And so this kind of manipulation is useful if you have a data set that only has, say, one column of information and you want to put it into a classifier. You might have to do this kind of manipulation, make it 2D, and then feed it in. We can also reshape. So the really nice thing about both transpose and reshape is that you can imagine in C making a big matrix of variables and saying, okay, I need to transpose this. Making a whole new matrix that's the same size as the old one and element by element copying. NumPy doesn't do this. NumPy keeps track of indexes into a matrix and then handles reshapes for you. So typically reshaping and transposing don't make copies of things. This is really nice for being quick and dirty on something small like a MacBook Air, like I'm presenting on right now. It lets you do a lot of things that might actually end up burning you, but very smart people thought a long time about the underlying structure of the data and handled it for you. So we can get the shape, and we can also reshape it. So when we do a reshape 5 by 3, fundamentally what we're saying is take this 3 by 5, and I want to transform it to be 5 by 3. And there are rules and structure into how this is done. In this case, it basically takes the first 3 elements, says, hey, this is the first column, takes the next 3 elements, says it's the second column, takes the third, this is the next row, 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 row. And without getting into too much detail, the underlying structure of NumPy is flat in memory. So what's really happening under the hood is when we say it's 5 by 3, NumPy is saying one row is the first 5 elements, second row is the next 5 elements, third row is the next 5 elements. And when we change to 3 by 5, NumPy just says, oh, well, it's 1D in memory, so I'll change the strides to be 3 elements for a row, 3 elements for a row, 3 elements for a row, 3 elements for a row. And it does this without copying your data, and it's very, very nice most of the time. Every once in a while, you'll get a copy, and then something strange happens. But we'll talk about that a little bit. So we can index by an array of integers, fancy indexing. This is the thing that can cause copies, but you shouldn't worry about this too much unless you get weird memory blowups. Then you start looking for these things. Basically, all it means is you can permute the array kind of on its own. You can say, I want to take my old X, I want to make the third row the first one the second, and the 0th one the third. And it kind of shuffles things around and gives you the result. Once again, that's just looking at different portions of memory that's all laid out in 1D under the hood. And NumPy is very deep. There's a lot to know about NumPy. But at a broad level, all you really need to know is these kinds of basic things. What it is, how to do reshapes and transposes, how to slice things out and select them. We'll also go into SciPy sparse matrices. We don't use these much in the tutorial, but you can imagine for something like text. Think about how many possible words there are in the English language. There's a lot, right? So if you wanted to represent a data set in a 2D array densely, you would have every single row would have the number of entries of the whole English language, and the sentence would have like 10 or 20 words. So there would be like 10 or 20 ones, and who knows how many zeros, maybe a million, maybe a billion, who knows. It's very wasteful. Like, we don't need to know the zeros. We only need to know the ones. So that's kind of the representation that sparse matrices let us do. We say, in general, things are empty, so why don't you just tell me what's not empty, and I'll operate on that. And there's, under the hood, there's a bunch of different ways to do this so that things can be fast. But At a high level, it's very similar to NumPy. So we can create some random array with a lot of zeros. So we create a random array first, and then we say, hey, if you're below 0.7, set you to 0. So now we see that we've got a big matrix still, but a bunch of it is 0, and it's not really informative or useful. So we can actually say, well, it's kind of wasteful to represent this whole array in memory and keep it there. Why don't we just represent the numbers that aren't 0? We can do that. And now we can see it's saying, oh, 0, 2 right here is not 0, and 1, 0 is not 0, and 1, 2 is not 0. And so it's kind of like a list of indices and values. And there's kind of different ways under the hood that this is represented. Depending on the way you access your data, there's different ways to lay this out so that it's faster or slower. But typically, scikit-learn will use CSR or something called CSC, which is compressed sparse row and compressed sparse column. And mostly that depends on if you're accessing rows like this, or if you're accessing columns like this. There's also a couple of other formats that we'll briefly go over here. You can also convert back to dense. Once you have a sparse matrix, you can convert back to dense and look at it. In some cases, like if you wanted to have the whole of Wikipedia in memory, if you tried to densify it, bad things would happen. Even sometimes the sparse matrix doesn't fit in memory, and then you have other problems. But those are the problems we're not going to talk about today, except for at the very end of the day today. So CSR can be efficient for computation, but maybe not as good for putting new elements into the array. You can use something called an LIL matrix, list and list. Convert those back to arrays. Convert it to CSR. You can kind of convert between all of these formats. There's paths back and forth. And there's a whole bunch of others. And normally when you get into which SciPy sparse matrix is the most important for my problem, you're optimizing. So you're fundamentally, you think you have a grasp on your particular problem, and you're trying to figure out how to make your solution faster or better. At that point, you start Googling and looking on Stack Overflow and looking at the docs and figuring out which one is the best representation for your problem. And for a lot of these, it's problem specific. We won't use it much more here. We won't talk about it much more, but it's important to know it exists because it's very, very, very wasteful to stick all those zeros in memory. So visualization is another really important point of machine learning. You want to be able to do things like give a presentation to a bunch of people and show them diagrams and show them plots so they know what you're talking about. We use matplotlib, which is an awesome package. Once again, one of the reasons we're all here, using Python to do science. And matplotlib, Jupyter Notebook has something nice called matplotlib inline. And this is a Jupyter magic or IPython magic. There's a whole bunch of these kinds of things around. You can look online for some of them. This is one of the most useful ones because it puts all of our matplotlib plots from somewhere else into the notebook in front of us. So we can import some plots, plot a line, shows up down here. We can do scatter plots as well. Things like this. And we'll be doing plots all throughout, so I'm not going to spend too much time talking about the different styles of plots. We can also look at shapes of things and plot diagrams. Nice things like this. We can do contour maps, 3D plotting. And there's a matplotlib gallery that has huge, huge, huge numbers of examples. And most of the time, this is the way, if you want to do a fancy graphic, this is one of the ways you want to learn. You want to look at the way people do plots for both the matplotlib gallery and also the scikit-learn gallery has a whole bunch of examples of ways to plot data that maybe you can say, well, my data is not digits, but I kind of want that style of plot. And then you can take that example and crib it and manipulate it and plot your data the way you want. We also have percent load magic, which is basically you can have a cell that just has this top line in it, do percent load from either some file that you have locally or some remote Python file. It'll load the whole thing into the cell, and then you can run it. And get cool plots like this. So this is one of the examples from matplotlib. There's a whole bunch more. So with that, I will conclude 1.2. Now that we're refreshed, we can move on to the data representation for machine learning. We've discussed it a little bit, but now we'll see it graphically and in some detail. We want to represent our data in an efficient way, be it a sparse or a dense matrix. Fundamentally, we think of it as a 2D array. That 2D array, from before the 5x3 or 3x5 matrix, in scikit-learn, we would say that the array is samples as rows, features as columns. What that means is every example in our spam, no spam example, one email would be one row in the matrix. Another email, another row in the matrix. Another email, another row in the matrix. And depending on what features we have, which we'll talk about how to make features and how to generate features, that would be some number of columns. So in our case, the very simplest idea is we have every word in the English language, and we put a 1 every time we see a word in an email. Our features are every word in the English language, and we basically just count. We say either this word was there or not, or this word was here twice or once or whatever. You can do this for a whole host of problems. Say I have an image and I extract I have some really smart feature that says there is a cat in this image or not, or there is a dog in this image or not. Maybe you only have two features, right? You have an image and it says cat in this image, dog in this image, or both. And from there you try to make some classification like is cute, is not cute. That's one way to do machine learning. Now you have to figure out how to get the oracle that can see cats and dogs, but that's kind of a separate problem. You can also use features to kind of encode domain knowledge. So in our examples of time series, you could very well have someone who has analyzed the stock market for a long time and knows that the price of orange juice 2 weeks ago somehow affects the price of cattle today. There could be a feature that is price of cattle 2 weeks ago, and that could be one column in your matrix. So features are both a way to represent the data and a way to encode domain knowledge. And depending on what style of machine learning you do, you'll put more effort into engineering features and going complex that way, or you can put more effort into engineering the model and the algorithm that underlies the decision. Sometimes you end up doing both. So, end samples. One easy way to think of this array is a CSV file. So most people have dealt with CSV at some point. It's row, 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 and some commas that separate them. And if you're lucky, someone was nice and all of the fields have the commas stripped out. If you're unlucky, someone didn't escape the commas and you're in this weird place of is this comma a delimiter or is it part of the data, and you do data cleaning. We have actually some examples of this later on in the day this morning. Pictures, if you take a 2D picture and say it's, in the case of our digits examples that will show 8 by 8, you can flatten the image out to 64, and then each image becomes a 64-dimensional vector. So each digit has 64 dimensions, and all it is pixel values for top left corner, next, 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 next. And in NumPy, that's simply like load the image and then dot reshape to one dimension, or something dot ravel or dot flatten. And we'll see examples of all three of these later on. You can represent video in the same way, even though it may or may not be informative. You could take the whole video, flatten it out to like, I saw this pixel at this time, and have a really long thing. Features are usually real valued. They may also be discrete valued in the case of the words example. Is this word here or not? And you can take advantage of this if you're trying to save memory. If it's Boolean, you don't need to use 64 bits to represent it. You need 1 bit to represent it. So these are the kinds of trade-offs you get into if you have a lot of data. So let's go to a simple example. One of the simplest ones that scikit-learn has built in is called the iris dataset. Basically, a long, long time ago, someone went out and measured the petals and sepals of an iris, and based on that said, I want to categorize these 3 types of flower. So I think we have a diagram of petals and sepals. I'm not seeing a great picture here of it, but it's 2 different parts of the flower. So someone went out and measured this and said, based on these, I think we can separate Iris virginica, Iris versicolor, and Iris setosa from each other. So that's a classification problem. If we want to design an algorithm to recognize the iris, what might the data set be? I just gave away the ghost on that one. Basically, that would be some measurement of the particular thing that you're looking at, and that would be a feature. Like the sepals are this long, that's one feature. The petals are this long, that's one feature. The color of the petals is this, that's one feature. And based on that, you think you can differentiate between different flowers. For scikit-learn and for most problems generally, there must be a fixed number of features. So if you say, I'm going to look at the color, I'm going to measure the length of the petal, I'm going to measure the length of the sepal, you have to do that for every flower, or you have to fill in for a particular flower like did not measure or something. But fundamentally, you have to have values for each feature because it is a 2D matrix. So loading the iris data with scikit-learn is straightforward. It's built into the library. The features are sepal length, sepal width, petal length, petal width. And we have 3 classes to predict. And there's lots and lots of examples on scikit-learn's gallery using this data set because it's nice to visualize, it's pretty simple, and it's intuitive. Yeah, so here's if you want to know what a petal and sepal is, petals here, sepals here. So someone measured those 2 and measured color and a number of other things, but you can even just use the petals and sepals to figure out which flower is represented. So we have a number of helper functions in scikit-learn.datasets to load various small testing datasets. And here we can load iris. You can see what data is available by looking at iris.keys. There's a description, there's some data, there's the target, which in this case is a numerical encoding of the name of the thing. So instead of saying Iris virginica, it might be 2, and Iris setosa might be 0. We've just taken the names of the thing and mapped it to an integer label. We also have the actual names, the mapping between them if you want to inspect, and also the names of what the features mean. So you have a 2D array, you have the columns, and we have the names of the columns so you can kind of inspect and figure out what they mean. So there's 150 samples, 4 features, length, and width again. We can look at the first example. The first one had a sepal length of 5.1 centimeters, 3.5 centimeters, 1.4 centimeters, 0.2 centimeters. If you're an expert in flowers, this might mean something to you. I am not. So I take this data and put it into a classifier and say, this looks great to me. And that's one of the other powers of machine learning, is depending on your style, if someone else has extracted features, you don't necessarily need to be an expert on the data and the features that were extracted from it. You might have to be an expert in the algorithms that follow it or how to represent the data in a simple way in memory, but you don't necessarily have to be an expert in the domain that the data was collected in. Very, very useful. Look at the target attributes. We can see that everything by default is ordered. So we can actually see where this could potentially be a problem. Remember, I was talking about training and testing very, very explicitly and very, very often. What is one of the easiest ways to fool yourself? Take this data set, slice off the last 10, 20, or 100 values and say, oh, this represents the distribution of my data. Well, if you sliced off right here, what would you get? You would train on all 0 and all 1, which is fine, but then your test data is all something you've never seen before. You're probably going to do really poorly. And you would imagine in the real world, you would kind of care about, in a 3-class classification problem, having some number of all 3 of those classes. So inspecting your data is important, and even just the basic data loading and figuring out what is training, what is validation, always kind of worth it to sanity check and look at your data and make sure what you're training on and what you're thinking about is what it's supposed to be. So we can go here, look at the target names. So in this case, if we sliced right here, we would have never ever seen an iris virginica, and then we would try to classify it. That's typically going to go poorly, not recommended. We can also plot some of this stuff. And we plot in 2 dimensions the 0th axis and the 0th feature and the first feature, which should be sepal length and sepal width. We see a nice 2-dimensional plot where very clearly setosa is, or should be, very easy to separate from the other 2. So what that means is it should be easy to classify setosa if our 2 features are sepal length and sepal width. It's kind of off on its own. The other 2 are kind of muddled, and it might be hard to classify them using these 2 features. So this actually brings up an important point. If we see a plot like this, what does it mean? It means we probably want to add another feature that's good at discriminating virginica and versicolor, because then we can hopefully get another dimension where virginica and versicolor are just as easy to separate as this. And then we have one dimension where we can figure out, oh, it's setosa or not setosa. We have another axis where we can figure out it's virginica or not virginica. And then from there, we have enough information to kind of separate all 3 classes. You usually won't be so lucky as to be able to plot in 2 dimensions and get something informative. But if you are, it's a great idea to inspect and use that to further your ideas of what data you need next. So now, I'm tired of talking, so let's do a quick exercise. In the above script here, try changing the x-axis, or the x-index and the y-index. See what happens. See what the plot looks like. So there should be up to 4 values here. So maybe we could change this to 3. And, well, let's be ordered about this. 2 and 3. And see what happens. Okay, we can see that virginica and versicolor have kind of separated themselves out. So if you imagine we have something that can draw lines in 2 dimensions, which is one way to think of classification problems, it should be a lot easier to at least get most of the virginica and versicolor correctly. In addition, it looks like setosa is once again kind of way off on its own. So play around with that for, I guess, a minute or 2. I have one more section to go over, and then Andy will take over. And I will try not to beat the training and testing data too much more. Yeah. So while you're all doing that, I'll go ahead and just mention that we have a bunch of packaged data. We also have a number of wrappers to extra data. We have ways to generate toy data. We use this a lot in the tests. We generate some distribution of data that should break or make the classifier work, and we use that to make sure our classifiers mathematically aren't broken. Usually this works out well. Every once in a while something weird happens, and then we add a new test. In general, with scikit-learn, you don't need data that has to be packaged or has to be downloadable. You can do whatever you want to your data up front. You can read from a database, you can pull images off of a camera, whatever, and write either a series of scripts or a pipeline or something that transforms your data into this 2D thing of samples, features, and then scikit-learn will deal with it. This is one of the strengths of the API, which we'll talk about a lot throughout, and you'll see good examples of. try to make the API as simple as possible and as clear as possible. This is how you represent your data. Here's a model that can deal with that representation. Also, IPython notebook is really nice because you can kind of start typing, hit tab a whole bunch, and it'll tell you what your options are and what's available. So, something like this. At this point right here, many data sets are large. We don't want to kill conference Wi-Fi, is why we sent numerous emails, fetch the data beforehand, because we're trying to be nice about this. We also have other data sets. Digits data set in this case. I'm going a little fast to see if there's something we didn't cover before. Once again, you'll see that everything's numerical. In the case of digits, there's 10 possible digits, so we have 0 through 9 as labels. And if you actually take one row of this and reshape it back to 2D and plot it, you'll see an image of a digit. And up until not too long ago, recognizing digits was actually a fairly, not hard, but not easy problem that people cared a lot about. Anymore, we've moved on from digits to more complicated things, but it still makes a really great example, and it's really nice to visualize and think about. And it also shows you how to deal with image data well. Oh no. So this is kind of in-depth NumPy guts. You probably don't have to worry about this too much. If you do, you're in the realm of big data. Best of luck to you. Yeah, so here's an example of plotting the digits out in front of you with the labels for them down here. As you can see, they're kind of hard to recognize visually. Like, this is kind of weird looking. This is what, I don't know what that is. So it's also important to visualize your data and see if you're asking for something crazy. At least for the kind of problems that I work on and try to solve. Pretty much the gold standard is humans. Can a human look at this data and separate it and make sense of it and do something with it? If they can't, maybe your input is garbage. Maybe you need to add more features, or maybe you need to clean up these digits so that they aren't blurry and weird looking. Maybe you have some things that are just mislabeled. They're wrong. So you're never going to get 100% accuracy. You're always going to be somewhere in the 90% range. So if you get 100% accuracy, you should be very suspicious in that case, because there's fundamental noise in the data you're feeding. We also have other generated data sets that look really cool when plotted in 3 dimensions. You'll see a lot of examples of these in the manifold and unsupervised learning stuff that Andy will talk about in a little bit. Okay, yeah, we still have plenty of time. So we can do an example with the face data sets. I won't scroll down to the solution and spoil it. You could try to fetch the faces and plot them, and we can take probably 5 minutes to go ahead and try to do that, and that'll take us to 9 o'clock, which seems like about halfway to our break at around 10. So take 5 minutes. If you want to just look at the solution and hack on it, that's fine. If you want to go from first principles and try to load it up, do that. If anybody has any questions or needs help, raise your hand and we'll come around. And I'll go to the next one in 4 or 5 minutes. And I'll also sit down for those 4 minutes. Okay, it's been about 5 minutes, so I'm back. and let's check out the solution. This was actually pulled in using the load magic. And also I have the slowest laptop in the room. I would almost guarantee it. So if mine plots it, yours should too. MacBook Air 2011. Another nice thing about Scikit-learn is it works on a huge number of platforms, and we work really hard to make it happen. So if you have a problem on some weird platform, please raise an issue and we will try to fix it. So here you can see the Olivetti faces. It's another kind of canonical data set if you're working with image processing and the ideas behind images. Just a whole bunch of pictures of a whole bunch of people in various poses and various lighting. They're pretty centered, which is actually nice for faces. Face data in its natural state is usually just horrible. People in all kinds of different poses, lights on, lights off, glasses, no glasses, beard, no beard. This makes the job a lot harder. So this data set, because it's kind of cropped and centered and very regular, someone went through and really cleaned it up nicely, makes it easier to test ideas about either image processing in general or faces specifically. All right, so now we can go on to 1.4. And I'll close a few of these. All right. So, training and testing data. I swear I'm not going to hammer on this too much more. That is unfortunate. Can I zoom out and get it to...
Use the image tag with width equals to 100. If you do HTML.
Oh, yeah. No way. Yeah, so I zoomed out briefly because I want to show this diagram. Basically, when I talk about training and testing data, this is what we mean. So we have all of our data, just a big block, right? And this is actually a little misleading because in the Scikit-learn representation, this would be samples, this would be features. But really what we're talking about here is this is like a progress bar of all of our data ever, that we ever collected. And at some point we want to take a chunk of it, cut it off, and say these samples we're going to hold out. We're going to hold those separately and pretend like they're new data coming into our system. So then we can test ourselves and make sure we're doing okay. Because there's nothing worse than thinking you're doing okay, getting data, and finding out that you're doing very bad things. And we have a huge number of notebooks later on and in the afternoon that go into detail of like what tricking yourself means, how you can fight against it, different metrics for finding out that you're tricking yourself. And this is kind of the big problem in machine learning is most algorithms are very good on the training set. Like if I look at 10 emails over and over and over and over and over again, and someone says, this is spam, this is not spam, this is spam, this is not spam, and I read those 10 emails and that's it. And someone sends me a new email that I've never seen before with words I can't read. How do I deal with that? How do I figure out if it's spam or not spam? I can't. I have no concept. There's no common ground between the data I've seen and the data I've not seen. So most of machine learning, and especially trying to get real systems working, is bridging this gap, figuring out how to make your training data resemble the testing data as much as possible, how to simulate testing data, and make sure you're doing really well before you deploy in the field. So I'll zoom back in, or try to. All right. Well, all right. Here we go. So we can also go through a brief example. I won't talk too much about the API because we're going to talk about that next. But at a high level, it'll show you how straightforward using Scikit-learn is. We load the iris dataset again. We pull in some classifier. We don't even really have to think about the underlying algorithm too much, at least for this example. As I said, real-world systems can only operate on data that we have now, can't operate on the future. So when new data comes in, we want to do things with it. One important and subtle point that we kind of touched on earlier is that if all of this data is coming in kind of a sorted order, like all of my labels 0 are together, all of my label 1 are together, all of my label 2 are together. Just slicing it as we have in this diagram right here is actually a bad thing, because then we're cutting out a lot of a particular label and none of other labels. So normally what you would do here, take all the data, jumble it up, and then randomly select out of that what is going to be training and what's going to be testing. And scikit-learn has a bunch of nice helper functions for this. When I mentioned that there's a lot of papers that have to be retracted because people mess up the methodology, most of the time it's because they wrote their own training, testing, split code and didn't quite get it right. So if you write your own training and testing split code, make very, 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 very sure that you're not referencing the same underlying data, or there's not repeating data in the test set, and there's a lot of stuff involved. And some of it scikit-learn handles for you. Some of it you kind of have to inspect the data yourself, and it's a problem by problem issue. So back to the data. We talked about this proportional splitting thing, and so here's actually a visual example. Whole bunch of zeros, whole bunch of ones, whole bunch of twos. Shuffle our data. So now our labels and our samples together have been jumbled around. It's another important point. If you jumble your labels and not your data, then the mapping from data to labels is now broken and your classifier won't work. I've done this a lot. That was a question.
So with that, you're still maintaining the relationship between the data and the feature.
Yeah. So the comment was we're still maintaining the relationship between the data and the feature, because ultimately we think there is a mapping from the data to the label. And if we don't have that, there's nothing to learn. Really, not to get into too much detail, but it's kind of inversely related to concepts in cryptography, where basically we want to obscure information versus in machine learning, we're trying to pull information out. We're trying to find information and kind of lump it together. So if we destroy information by randomizing everything, we've destroyed the mapping and the information that we're trying to learn. So there's some subtleties related to this, but at a high level, you can kind of look at this, or in the next example, we also show using train test split. Train test split has some options to shuffle for you, and normally you're going to want to use this because it keeps you from writing this hundreds and hundreds and hundreds of times and messing it up the 101st time. So now we have training and testing. We've split them with a training size of 0.5. So 50% of the data is training, 50% is testing. You can also provide a random seed or a random state object from NumPy so that your scripts remain deterministic, because there's nothing more frustrating than running your script 3 times and getting 3 slightly different classification results and not knowing where that tolerance is coming from. And you'll notice in the scikit-learn source code that random states are everywhere because we want things to be deterministic, deterministically random. So here's a quick example of the scikit-learn API. We just have some classifier that we imported earlier. We fit, we predict, we look at the percent that are right, 96% accuracy. That means we're classifying pretty well. This is test. So we were actually simulating new data coming into the system here. If this had been train, we might get 100. We might do really well, but then find out that our testing fraction is actually really poor. And that's something called overfitting that we'll talk about a lot later on. So we can also visualize correct and failed predictions in 2 dimensions here. Most of our errors occur where things are kind of jumbled together. This relates back to most classifiers trying to draw a line in some space. It may be 2-dimensional, it may be n-dimensional, but typically you're trying to plot out boundaries and say, if you're over this boundary, you are this class. If you are over this boundary, you are this class. And the way that you draw that boundary is kind of the mathematical guts of the particular classifier that you're using. And Andy is going to talk a lot about the different classifiers you can use and the different ways that you can pick the best one for your problem. So with that, we are officially on to 2.1, and Andy will take over.
All right. So now we get a little bit more to the meat of all of it. And we're going to start with supervised learning methods, in particular classification. So as Kyle mentioned earlier, this is if you want to predict something like a categorical variable, like a class label for each data point. So, and we had examples like spam classification, or classifying from an image to a digit, or classifying the iris data set, like measurements of sepal and petal, then going to the species of iris. So from now on, all the notebooks will start with something like matplotlib and numpy import. Before we go to any of the actual data sets, we're going to use a synthetic toy data set, make blobs. So this is basically just random Gaussian blobs in 2D space. We told it, so by default it makes 100 data points, each with 2 features. They look something like this. And there's 2 classes here, 0 and 1. As this is a 2D data set, we can very easily plot this so we can see what it actually looks like using plt.scatter, doing a scatter plot. So this is our data set here. So there's 2 features. This is the first feature. This is the second feature. There's 2 classes, red and blue. I really like to use 2D data sets for to demonstrate how algorithms work. And we saw the 2D plots on iris. The problem is, this is nice to explain. In the real world, this will never work. If you have iris and you have 4 features, you might plot most of the combinations. If you actually do some machine learning, there will be hundreds of features, and you will never be able to plot a nice plot like this. But it's nice to see what's going on, on these toy examples. All right. So, as Kyle said, we need to split our data into a training part on which we build the model, and the test part that we use to evaluate how well we can predict on new unseen data. And we use the train test split function that Kyle just explained. So we have 100 points here. They're just in this 2D space, and we split this up into 75 samples for training and 25 for testing. And now we want to build a machine learning model with scikit-learn that classifies red versus blue. And the scikit-learn API is very much built around this split of training and then predicting and evaluating our model. So we start off with xtrain, which is our training data. So it's a NumPy array of number of samples times number of features, and the training labels, which is just number of samples times 0 or 1, encoding red or black dot. And we'll use that to build the model. And then we want to use the test data to make a prediction, and finally evaluate how well we generalize to the test data. All the algorithms in scikit-learn are implemented in objects. So we call these estimator objects that have a particular interface. The simplest algorithm I want to start with is logistic regression, which is a classification algorithm. And so this is just one example. Don't worry too much about what the algorithm actually does for the moment. So the interface is usually you instantiate the object first, so you get you instantiate the class first to get an object. This is when you can set options of how you want the model to work. We're going to go into this in more detail later. But now you have this logistic regression object, and you can build the model using the fit function. So this is one of the fundamental functions in scikit-learn. And you give it your data, your training data, and your training labels. So I love Max. Sorry. So here again, xtrain is 75 samples with 2 features, and ytrain is just 75 numbers. and we give it these two NumPy arrays. And this builds the model. And the model will be stored in this classifier object. And now we can, and so pressing Shift Enter built the whole model. And now we can use this model either to predict on the training data or on new unseen test data. And to predict, we use the predict method. And these are really the two core functions: fit to build the model, and predict to apply the model to new data. So now I give the predict function xtest, which is the data, the features of the holdout points, and I get back a prediction. So these predictions are now 25 zeros and ones. So for each point in the test data set, I get whether the model thinks this is a red point or a blue point. Oh, yeah. And we can compare this against the ground truth data set, and it looks fairly similar. There's like one here where there's a confusion, and there's one here where there's a confusion. But it looks like the model did a pretty good job in predicting on the test data set. We can measure how well we did in a more quantitative way by just seeing what fraction of the labels is actually correct, and it's 92%. There's a convenience function that models computes how well a model does. It's called score. This is another function that is available for all supervised models. And you give it the test data, and it'll make a prediction on this test data, and it'll compare against the test labels. And this will compute exactly the same thing. So it does a prediction, compares against the ground truth. So we have a 92% accuracy here. It's often also helpful to see how well you do on the training set. So actually here in this case we do the same on a test and a training set. Often you'll see that you'll do much better on a training set, which is what Carl talked about in some depth. So now let's go into a little bit more detail about the actual algorithm of this logistic regression. What it does is it's one of the so-called linear models in the linear model package. And what this means is basically it computes a line in 2D. And we can plot what it does. I wrote a small helper function here, plot 2D, the separator. It'll show us what a classifier does. And you can see here that it learned this line. This is what the classifier learned. What is the difference between blue and red? And so everything below this line, the classifier thinks is red, and everything above this line, the classifier thinks it's blue. And that seems like a pretty reasonable job. Again, this is very nice to visualize this in 2D. You can basically never do this for any actual real-world data set. And you think, okay, you could have drawn this line yourself. If you have 100 features, you could probably not, you don't know how to draw this line. So if you have more features, this will be like a plane, a hyperplane, a linear thing in high dimensions that's much harder to understand than this line, and it's very hard to draw these yourself. But here on this toy data set, you can see what you're doing.
In some languages like R, you can specify a model for logistic regression of formula, so that maybe one variable could be related in X, but the other is related in X squared. Do you have any info like that here?
There's no formula method, and we don't have that. You can
Create another variable?
yeah, you can create. So yeah, we have. If you want to do polynomials, we have feature extraction things that will create another variable for you. But we basically, all the supervised models assume that you have this number of samples times number of features, and these are the features that you're going to use. Yeah. So, oh, there's a package called Patsy that lets you do formula methods.
Sorry, called what?
Patsy. Yeah.
That's not a yes. Vector
Hmm?
Is that a support vector?
That's logistic regression. They do very similar thing. So linear support vector machines, they draw also lines or hyperplanes, and logistic regression also does that. They just are slightly different in the mathematical details, but usually they basically have the same result. So I don't think we have the mathematical formula for this here, but But basically what these linear models do, like the linear support vector machine or logistic regression, is for each, we'll go into more detail about this later. Okay, for now, let's say it draws a line. I think we'll go into depth in the afternoon about how linear models work. And there are some things that we'll explain in the afternoon that are estimated from the data, like the coefficients and the intercept. These are the things that specify this line. And everything in all scikit-learn models that is learned from the data ends with an underscore. So if you do autocompletion, so these are the things that are learned from this data that we'll explain later. But so basically, if you do autocompletion, then you can see everything that ends with an underscore was learned from the training data. The other one that you have here is classes, which will be 0 and 1, the two classes that exist in this data set. Okay, but the cool thing about scikit-learn is that it has a very consistent interface. So we can use another classifier, and it will be just the same thing. Another kind of simple to understand classifier is the nearest neighbor classifier. In a way, it says, if I have a new data point, I'll compare it to all of the training data points, and I'll give it a label of the closest one. That would be one nearest neighbor. It looks at just the nearest point to it. Okay, we're going to do that here. And so again, it's exactly the same thing. We import the class. We instantiate the model. Here we say, look at only the nearest neighbor point. And then fit the model using the training data and training labels. Then we can scatter the result and see what what it is that the classifier learned. And you can see that it's much more complicated than just a straight line, because for each point it'll learn, is this point closer to any blue point or to any red point? And you see here, because there's the blue point in the red point, next to the red point here, there's like a small island of blue here. So you can also look at more than one neighbor, for example, by setting the n neighbors to 3. That will take the majority vote of the 3 closest neighbors. And so here, I just plotted what it looks like. We can also use the predict function to, so k and n also has the, I call it k and n, right? Yeah. The predict and the score functions. So it actually does perfectly on a test set. All right, so now I want to do a short exercise with you where you apply this to the, did we do that yet? Yeah, apply the k-neighbors classifier to the iris data set. So you can load the iris data set from sklearn datasets, load iris. And then you can split the iris dataset and apply the k-neighbors classifier. And you can see how varying maybe you can try a couple of n neighbors parameters and see how they do on the iris dataset. And I want to give you 5 minutes for that. Or are there any questions so far? Okay. Yeah?
So the dimension for the screen split is 75, 30,
75-25. But you can also, where is it? That's slightly arbitrary, and we're going to go into much more detail about how to do this better, I think, after the break. But yeah, so you can just do Shift-Tab here, and you'll see in the docstring you can find this. So here test size is set to 25%, but you can also just put in test size and make it 30% or 10. Okay, so solution looks something like this. No, I need to split a data set. Whoops. Okay, so yeah, the solution looks something like this. We get a train test split, apply it to iris.data, which is the data in the iris dataset, and the target. So now we have training and test labels and training test data. We instantiate the model. Here I set number of neighbors to 3. We fit the model. Then we can evaluate it on the training data, the test data, or and also just get the prediction on the test data here. And with the 3-class classification tasks, so we have 0, 1, and 2 outputs. And you can change this up a little bit. And so what you can see here, for example, is that if you look at only the closest neighbor, the training performance will always be perfect, because if you put in a point that is already in a training data set, it remembered this point is this label, and so will just predict the correct label. That's what, so if you do nearest neighbor classification, the training set performance is not really that informative, because it will just remember for each point what the label was. Okay. Any questions?
How would you show the separator line?
Yeah. Okay, so maybe I should have. So this is kind of the point I tried to make earlier. So you can really only plot this for 2D data sets. So this means this is kind of good to get the concepts, but you can never do this for any real data set. So even for the iris data set, you cannot really plot this. Well, you can slice it, but that's not. You can slice it, but you cannot project it. So you could fix a function of like the sepal width, and then for this particular sepal width plot, and like, okay, I guess if you do a 2D plot, you need to pick 2 other data points, and you could maybe plot this slice, and but that's going to be very hard to kind of visualize in a way. And if you have 50, then if you have like 48 planes along which you slice, doesn't really work. So, yeah. Pardon? Sorry, I didn't catch it. We didn't shuffle the data, you mean? Oh, so train test split shuffles the data. Actually, there's a new thing that I did. Well, okay, yeah. We'll go into more about kind of what train test split does and what better things after the break. But yeah, train test split shuffles the data by default, so that this example actually works. Otherwise, if we didn't shuffle, we'd have 0% accuracy. All right. More questions? Yeah.
How do you decide on the number of neighbors?
After the break. Very good question. So this is like, clearly, it's hard. So, I mean, obviously the intuitive thing is pick the one that's best on a test set, right? That's sort of what you would do, but that's problematic. And we'll go, after the break, we'll go into why that's problematic, and yeah. But that's that is the question that machine learning researchers worry about most of the day. How do I pick the parameter for my classification algorithm or my regression algorithm? Okay, but okay, now let's.
So you've got your own kind of data format for storing your sample data sets. Do you recommend using that instead of data frames from pandas?
No. So we have these bunch. So the question was, we have this kind of custom format, these bunch objects that have data and target, and they are really, don't worry about them at all. They're basically just a dictionary. People ask us, how do we create a bunch object? And the answer is, don't. They're just sort of, so that we have one object to load which has this description, which is a string. But really you should worry about bringing your data into a format that is a NumPy array for the data and a NumPy array for the labels. And you can use pandas for that. We're not going to talk about pandas really. Pandas is a good way to get this, but you should do something to your data so that it's NumPy array, number of samples times number of features. And if you have a supervised algorithm, you should get a NumPy array of classification or regression labels. That's all you need.
You will not find the dominant class among the K
if k is 2, then I think it'll just randomly pick one. So if there's a tie, it'll just randomly pick one. So it's not better than 1, actually.
Maybe just pick odd numbers.
Hmm?
At least pick odd numbers at the time.
Yeah. Well, if you have, you don't need to pick an odd number. I mean, if there's 4, it could be 3 to 1. Maybe 2 is not a good choice for 2 cluster, or maybe 2 is not a good choice. Was there another question? Okay, let's go to regression. The good thing about scikit-learn is that all the interfaces are the same. So this is going to be exactly the same thing as for classification. So again, in regression, we're not trying to predict a class variable, but we're trying to predict a continuous output variable. So again, we have our input data, which is like number of samples times number of features. Here we're going to do something very simple, where there's going to be only one feature, which is just going to be a linear, like just one number. And our data set is just going to be sort of a line. It's just going to be linear input from -3 to 3. So there's 100 samples with exactly one feature. And our output will be just some sinus function. I mean, more realistic examples of this are like, predicting stock market stuff. In predicting stock market, you might actually also, it might look kind of similar, or predicting how much a product will sell, what should be the price, how many of your customers will predict, will click on an ad or something like that. So you want a continuous output variable. And so this is the most simple example. So here, regression you can most easily plot in if you only have one input feature and one output feature. So here x is the input feature, and y is the output you want to predict. So it's like this wiggly sinus line. And we want to learn that. The most simple method is like linear method. We'll explain that in more detail later. But basically, this tries to fit a line or a plane to your data. And so we have one input feature. This is which was just the -3 to 3. But for scikit-learn, it needs to be number of samples times number of features. So we are going to use this numpy.new axis to reshape it so it's actually a 2D array. Currently, I think it'll work with a 1D array, but we're going to drop that support. So always use 2D arrays. So it's clear what are the samples, what are the features. Again, we use train test split to split it into training and test data set. And then we build the regression model. And as you can see, it looks exactly like the classification model. We import a class, we instantiate the class, and we fit it using the training data and the training targets, the continuous training outputs. And now we use the predict function. And then we can plot the predictions. So here, for each point, the blue is the actual data and the green is the prediction. And you can see that it learned just a line, so just a linear prediction. Because that's everything that this classifier can do. And so it picked up the slope very well, but it will be unable to model all these wiggles of the sinus. But I mean, the important part here is more instantiate the model, fit, predict. And now we can also do this on the test data set. So above this was the training data set, here's the test data set. And it looks similarly, I mean, it will just predict the same line. Again, we have also the score method, which will give us more qualitative evaluation. For the regression models, this is the R-squared score. So you should keep in mind in this, another very popular score is the mean squared error. Are we gonna? Okay, we're gonna talk about how to use that later. But like the default one is R-squared. Just keep that in mind. So another method, just to see that it's really always the same, the interface, is the neighbors regressor. This works exactly like the classifier, only takes the mean of all the k nearest points. So if you take number of neighbors equals to 1, it'll just predict the output of the nearest point. So it will just basically remember the training data set during the fit method, and then predict method, it will look at the next point. It's a bit hard to, I mean, here in this plot you can see that the predictions actually perfectly match the data because, again, you remember the whole training data set. So the green points are exactly on top of the blue points. And if we do the prediction, it actually, so this is the test data set, and on the test data set, it is, I mean, it's definitely better than the line. It's slightly too wiggly maybe, but it captures the slope and also captures some of the variation of the sinus. And we can look at the score. So this is, again, the R-squared. And this fits much better than the just the line. Let's see, the line that, yeah, 0.85. Here we got 0.95. So this was, again, like a very simple data set where you can visualize what the outcome is with one input variable and one output variable. Now, as an exercise, I want you to do this on the load Boston data set. And you can do so you can do this load Boston function, which will give you a bunch from which you can get the data and the target. And then you can apply linear regression and the neighbors regression and see what the scores are. Okay. Any questions so far? Yeah?
I was running that exact example and I got a score of 0.80, which seems 5% different from what you got.
Wait.
It's a reason for this randomness?
Wait, so for this?
For the one above, for the linear regression.
This one, you got
0.80 random space.
probably, I didn't fix the random state here. So this is like how the data is split. And also actually, maybe I was bad. Yeah, I was bad and didn't fix the random state here. So your data set is just a different data set. So here we have this, this wiggly thing, but we added random noise to make it like an interesting task. And your noise is different from my noise because I was lazy and didn't fix the random seed. Sorry.
Between the comparison between the k-nearest neighbors and the linear regression, it should be the same data set. So they are comparable.
Yeah. So, I mean, you ran this once, right? You ran this line once. This gives you some data set. But if you run this line again, then now it's in a different data set.
Thank you.
Okay. Oh, maybe one additional remark. So in this very simple example, the line seems very restrictive. In higher dimensions, it is not. So don't try to generalize too much from these small dimensional plots. Yeah. Lines are very powerful in high dimensions. You can, by the way, you can look at the description if you're interested in what this data set is actually about. This is predicting housing prices in several suburbs of Boston based on income, crime rates, and so on. And so here, you predict the price of a house in thousands of dollars. Okay, so the solution again is something like this. Here I now fix the random state to 42. If you want to get the same result as I do, fix the random state to 42. I again use the train test split function to split the data set. Then I instantiate the linear regression, and in the same line I call the fit function on train data set, look at the scores. You can see it did much better on the training data than the test data. And it did the same for the nearest neighbor regression. Here the nearest neighbor regression again does a little bit better. Maybe if I give it more neighbors, it'll even do better. Nope. Nope. Okay. Any questions so far? Scroll up. So I gave. Yeah, the problem is if I show the whole, I mean, this line is kind of long, but it's really, what it does is it shuffles the data, like the data and the target together, and then splits off some as training and some as test. So this is just doing a permutation of the data and then slicing. So this is like 2 lines of NumPy, but because we have to write these 2 lines of NumPy all the time, we have this small function to do it for us. Okay. Any questions so far? Okay. So supervised models, both regression and classification, train, predict, score. That are the important methods. So now let's move on to unsupervised learning. Kyle went into this a little bit. So one kind of unsupervised learning is the one where you get your data and you want to transform it into some new representation of the data. And there's no like target variable or anything like that. Someone just handed you some data and they said, learn something about this, basically. And then maybe you build a model. And if you get some more data, maybe you want to apply the same model to some new data that you observed. And you want to have a representation that tells you more about the data than the representation that you got handed initially. That's very abstract, and it's kind of it's a bit harder to understand than the supervised learning model where you have a clear target. It's also harder to evaluate. But let's see an example. So often this is used for pre-processing of your data. And something that I'd like to give as an example, it's probably not really actually learning, is just to normalize your data or to standardize it to have zero mean and unit variance. So that's a very simple pre-processing to get all of your features on the same scale. But you can think of it as an unsupervised learner that just learns the mean and the variance of your data. So we'll load the ARIS data set here. And so we have 150 samples of our flower measurements, and we have the 4 features. And we can compute the mean and standard deviation of these 4. And so for many of the linear models, it's helpful or important that these are kind of on the same scale. But you can see that the first feature has larger variations is larger than the other ones, but has smaller variation. And so the standard pre-processing you might want to do is a standard scalar, which removes the mean and then scales by the variance. It's again the same interface as for the classification. Mostly you import the class and instantiate it. And then you call the fit function. Here the fit function will just compute mean and variance. And then remember them for this data set X. It's an unsupervised model, so you don't give it a Y. Then, because you want to get a new view of your data, the method you are going to use is the transform method. So transform gives you a new representation of your data. And this just here, it's just centered and scaled the data. So it will have the same shape again as before. So now you have, again, 150 samples for features, but this time the scaled X has the mean removed, at least to numeric precision, and a standard deviation of 1. Okay, so that's a very yeah?
So kind of stupid asking this, but what's the value of making sure that all of your zero mean and standard deviation?
Sorry?
Why are you bothering to do this? It's not clear to me.
Why? Okay, so why do I want my features to have this property is the question. And so for some of the models, they work better with this. So, I mean, because of the so, okay, let me give you an example. So I had this, I mean, it's a matter of experience and practice when to use this, but it often helps. And let me give you an example. Let's say you have, you do nearest neighbor classification. So, so you look at the one nearest neighbor point, and your data is something where you have two features. They're on completely different scales. So let's say you have the same iris data set, but one of them you measured in millimeters or micrometers, the other one in centimeters. So one will be in the tens of thousands, and the other one will be like between 1 and 2. Now if you do nearest neighbors and you do just the distances, only the one that's in the tens of thousands will matter at all. Because if even the slightest deviation will be much larger than the one the other. But if you do the pre-processing, then the differences will be the same. So it will be on the same scale. Okay.
I have another question.
Yeah.
Why would you scale the data and not normalize them to make sure they are of the same range? Implicitly assuming some type of distribution.
Yes, so if I mean, I'm not saying do this for all your data. I'm saying this is one example of how to pre-process your data, or I'm more doing this to show you how to use this kind of algorithm. So, I mean, I'm not sure which normalization you mean, but so this assumes.
Normalize it to a range of -1 to 1 or 0 to 1.
Oh yeah.
So you make sure all your features are with the same range.
Yeah.
You scale them, you could still have
Yes.
feature values that are 10,000 or.
Yes. Yes. That's,
far out.
yes.
You can do that with the min-max.
Yeah. So there's the min-max scaler that does scaling between 0 and 1, but. So that's also often good. It depends on what kind of data you have. Sometimes min-max scaler is better. Sometimes the standard scaler is better. I mean, if you don't know your data well, try both and see which works better. I'm not, in no way I'm saying you should always do this. Also, the assumption here is that all features are of same importance if you do this. So if the one that's in the tens of thousands is just the small differences there matter just so much more than the small differences in the other one. If it's actually like, if one is in the tens of thousands, but a difference of 1 means the same as a difference of 1, the other one that's only between 0 and 1, then you shouldn't scale it. Scaling will completely mess up your stuff. So, yeah. This also assumes that all the features are kind of, the relative variation in the feature means the same thing. So, and any pre-processing you will do comes with assumptions. Yeah. All right. Yeah, actually I didn't. So pre-processing is an art, not a science. I just wanted to give, this is an example that's often helpful, in particular for linear models. Min-max scaler also is often very helpful. So one a bit more interesting example of doing these unsupervised transformations is principal component analysis. This transforms your data and is often used to reduce the dimension of your data. And so to demonstrate what this does is, I'll just create a synthetic example here. These are, this is just like an elongated Gaussian in 2 dimensions. And what simple component analysis does, it tries to find the directions that explain most of the variance in the data. And so most of the variance in this data set is along this axis. And then there's then it tries to find the next direction that has variation that is orthogonal to this one, which would be this. So basically, it tries to find the axis of the Gaussian that explains it, Gaussian. And applying this is exactly the same way as works exactly the same way as applying the standard scalar. You instantiate the model, and you fit it using just your data. Then again, if you want a new view of your data, you can call the transform method. It will give you the result of the principal component, which is the projection along this major axis. Now we can plot it, and we can see that it finds these axes and it does some scaling. It scales it in a way that sort of kind of by the covariance of the Gaussian in this direction. Variance, sorry. Okay, and you can see sort of, this is the same data set as this. You can see these like 4 points on the side there. They got projected here. And so now these two axes are kind of on the same scale, whereas here it was very elongated along one of them. Sometimes this is a good method to pre-process your data, not always. Often it's also good to reduce the dimensionality of your data. So if you, let me see. Okay, that's actually what we're going to do next. Okay, so basically what it does is it finds the rotation of your data, and then it tells you which of the axes in this rotation are the most important ones. Yeah?
Those are the scores, right, that you're plotting?
Depends what you mean by scores. They're also called loadings, and so it's like, it's the projection. It's the thing that you expect, and depending on which community you're in, you can call this one of 100 names. It's the projection along the axis scaled by the variance. Okay, so yeah, as I said, often this is used for dimensionality reduction. For example, we had this digits data set where you can plot a single digit as 8 by 8 like image, but you cannot plot the whole data set as we did here. You cannot plot a single digit in the 2D space because it's 64-dimensional. But you can try to find what are the major axes of along these pixels, and then you can look at the two most important ones. And I think that's what we're going to do here. So actually we're going to load only, why is this like, you put a fancy example in. Okay. Yeah, maybe we're not going to go through all of the detail of this, but we're going to load only the 6 first classes, so digits from 0 to 5. And yeah, we get 500 of the digits. And then we're going to plot them using... Why are we using this? Okay, this is... Okay, so we reduce them to 2 components. So n components equals to 2 means look at the 2 most important directions, and we call fit transform here. This is the same as doing fit x dot transform. So calling fit and transform method, only it's like a shortcut if we want to transform our training data set, and it's slightly faster. So this was like the digits, that's what they looked like. And then we can plot them in a fancy method projected into a 2-dimensional space. And here they're actually colored, and you have actually the digit there. And you can see that, for example, along these 2 principal components, so these are vectors in the 64-dimensional space. If you look, the most important ones, the zeros, are very far apart from the other digits because they look very different. But and the ones in the 4s also look quite different. But the 2, 3, and 5, they look kind of similar. Actually, it's also interesting, which is not in the example. You can also visualize these directions. So these directions are 64-dimensional vectors. Because they live in the same space. And the directions are stored in the components attribute. It's called, we didn't store our PCA object. So here, I just rewrote this shortcut to actually store the PCA object so that I can access the components. And this is sort of a picture form of the first principal component. And if you want, and then there's also a picture form of the second. And if you want, you can think about this, or you cannot think about this. There's another method that I want to. Sorry.
If you change the code, so I don't have that kind of separation. I just ran the code the way it is, the way you would get.
This one?
Yeah, we don't, some of us don't have that kind of separation.
So you did this, and it didn't work well. Yeah. Oh, you had this. So, okay, sorry. There was a last minute change to the notebook that I didn't know about. So if you use truncated SVD does the same as PCA, only doesn't remove the mean before. That's a really bad idea for this data set. I'm not sure who wrote this example. Doing a PCA actually gives you good separation. If you don't remove the mean before you do this, which PCA does automatically, then you don't get this good separation. Sorry about that. Can you make a note? Okay.
You said that PCA automatically removes the mean, but if you do the pre-processing step before you call PCA, are you doing that twice?
Yes, unless you tell it not to. I think there's an option. That's not the. Sorry, I have troubles with Macs. If you look at the doc string of the PCA, I think there's an option to assume that's already centered. But it's also removing the mean is free compared to like computational. It's basically free compared to doing the PCA. So I wouldn't worry much about computing the mean twice.
Because it won't hurt anything.
It won't. I mean, the only thing is, there will be it will introduce an error on the level of machine precision, and it'll cost compute mean. But I think these are things we shouldn't worry about in machine learning. Usually errors on the level of machine precision, at least on the raw data set, doesn't matter. On in the optimization, it might matter, but here I wouldn't be worried about it. Okay, so actually, I'm going to do one more thing, and then we're going to break because there's food out there until 10:30.
Could you go to view level, click view, toggle header, please?
The reason why I didn't do this because, well, I guess the notebooks are long enough. It's kind of annoying because you have to do this every time for every single notebook, and I hate that.
Sorry, can I see the component collage
Oh, okay. So you cannot. This components is number of components here. In this case, 2 times number of features. So here I selected the second principle of components. We start interpreting by 0, and then I take all the 84 features and I reshape it because it's an 8 times 8 digit, and so I can visualize this in the input space. This is just sort of a convenient way of representing something that is in this input space of images. There's also a mean. There's also a mean attribute to visualize the mean if you like. Okay. So PCA is a very simple method to go down to fewer dimensions. It's often helpful because it's like things that are. So basically, this tells you that this doesn't know anything about labels. You didn't give it any information about what are zeros, what are ones, and so on, and still separated out the zeros, which means this is really obvious in the data. But sometimes there are things not as obvious that you still could get out with a more complex method. And methods that project down to less dimensions with predictive visualizations are called manifold learning algorithms. And I want to talk very briefly about these. There's this great toy data set here that is used in 100 papers and will never appear in reality, which is this S-curve in 3 dimensions. So yeah, you have this, I mean, you can see what it's like. It's an S-curve. It's like flat along one direction and twisted upon itself. And it's actually, the data is kind of 2D. So you could think of it as being like a sheet of paper that it was originally, and someone bent it. And you actually care about sort of, you could flatten it out, and you could look at it much more easily, what the data means. The problem is if you do a rotation and projection like PCA does, this point and this point and this point will all like collapse on the same point, as this example shows. Actually, what it did, it took the second axis as the axis of variation and collapsed along the second axis. And so this lost a lot of information. You can use manifold learning techniques from the manifold module to keep this information. It will lose this curvature thing, but it'll hopefully recover the flat thing, flat part. One of them is isomap. So the interface here is basically the same. So the thing is, many of the manifold learning things cannot be applied to new data. Usually you give it all the data, your whole data set, and then it will compute something on this data set, and it will not be able to use it on new data. And for that reason, you have to call the fit transform method instead of calling fit and transform. Because you cannot transform arbitrary data, you can only transform your test data. Okay, and then it'll give you this. This is the transformation, the unraveled S. Actually, we did this already. Oh no, so you can use, or maybe you can use the isomap that we did here on, you can do this on the digits data set. And if you like, you can also use the t-SNE, which is in the manifold learning. So basically just load the digits and apply isomap and then scatter it and see if it's like, how it is different from this one. Okay, questions so far? Yeah?
Are we going to talk later on about how to handle missing data in the X or the Y?
Not really. We're not gonna. So there's some things in scikit-learn to handle missing data, but they're mostly completing your data and then doing something with it. And because most of the algorithms actually don't work naturally with missing data, and you have to redo them quite a bit. The trees would work, but we haven't implemented that. Well, from a machine learning standpoint, trees could work with missing data, but the ones in scikit-learn don't. Okay. Yeah, so I'll give you like 3 or 4 minutes to do the isomap on the digits data set, and then I'll show you the results, and then we can break. Okay, I think most people played around with it a little bit. So, I mean, so the n neighbors here is basically a free parameter that we just set to 15. High is usually better. And n components is because we want to go down to 2 components. And then we do isomap. Okay, and that's kind of what it looks like. So what's also really cool is t-SNE. It usually takes a little bit longer to compute. And tsne is really good for visualization usually. I mean, isomap is also mostly used for visualization. Yeah. And tsne is very good at finding like local structure stuff. Yeah, it might be slow. Okay. Are there any questions? Otherwise, yeah. Okay, so we'll break now. Ta-da! Okay, now we break until 10:30.
Can you show
The code. Okay, I'm sorry. Up. What were we? This was isomap. And actually, so n components tells you how many dimensions you want to get out. So actually, all the manifold stuff, because it's for visualization, defaults to giving you two dimensions back. So this x trans here, or maybe I put it. So is you have 101 digits, and each represented as 2 dimensions. Or did you have a specific question? Or the last kind of class of methods that we are going to look at is clustering, and then after that we'll do a quick repetition of all the interface things. So clustering is a different class of unsupervised learning algorithms. So we saw the dimensionality reduction and decomposition with PCA and manifold learning, where you give your data and you get out some transformed version of the data without using any labels. In clustering, you're trying to group your data. So you give it some data and you ask, are there groups here? And it's often used, say, in customer segmentation, where you want to have like a web shop and you want to find out, do I have like different parts of my customer base that behave differently, like I don't know, moms and teenagers and gamers or something like that. Or you may want to have news articles and want to cluster them together based on topics. And so in a way, this is kind of, you're trying to find a label. So you find a very simple representation of your data that is just sort of, this belongs to cluster moms, and this belongs to cluster news articles about politics. And so this is basically a discrete label that you want to get out. So you can think of this as kind of an unsupervised alternative to classification, where you want to get out a discrete output. And we're going to do this, again, on a very, very simple toy data set, which is, again, 100 points in 2 dimensions, just 2 blobs. Or 3 blobs. We only need 3 blobs. And this is our data set. And again, we do this so we can see what's going on and maybe understand a bit about the algorithm. Okay. How many groups are in this data? 3? Okay. I mean, I think 3 is a very natural answer here. And so depending on how you define groups, it could also be like maybe there's no groups in this at all because every point is like very distant from everyone. But okay, let's assume there's 3 groups in this data. And maybe in this 2-dimensional data set, we could, again, do this by hand. We could like circle them and see these are 3 groups. But in high dimensions, we probably can't do this by hand. So we need machine learning. But here we would hope that our algorithm recovers these 3 groups. Okay, so we want to apply some algorithm and find these 3 groups in the data. Okay. So the most common used algorithm for clustering, or one of the most common used ones, is k-means clustering. It finds, you tell it how many clusters you want. Let's say we know there's 3 in this data set. We just don't know what are these 3 clusters. And it'll find like centers around which the clusters form. These are like prototypes for each of the clusters. And okay, so we can build a model and actually get out the cluster labels by calling fit predict. We could also call fit and predict if we wanted to. So this computed the clustering and grouped the data. And now labels. I lost my toolbar. Ha. Okay. Labels are now numbers between 0 and 2 that say which point belongs to which group. You could also, for the trained data set, all the clustering algorithms have an attribute called labels, which also stores the cluster memberships for the trained data set. Now we can do a visualization. So we plot our blobs data set here, and we color them by the cluster labels we found. And hooray, it identified the 3 clusters. If it didn't, it would be a really bad algorithm. So now let's say we can't really look at this data because it's high dimensional, and we want to see how well did it do. And also, let's say we knew what the real clustering is supposed to look like. Actually, the make blobs data set, used it before, it has this Y, which tells us which blob everyone belongs to. And now we could do something like compute accuracy, which is just, okay, I used accuracy score here. It's the same as, so Y is the ground truth, labels is what the cluster algorithm found. And you can see they never found the same thing. And you can see why this is the case by looking at what's called the confusion matrix. So here's the rows correspond to what Y thinks the label should be, and the columns correspond to what the labels are that are produced by the clustering. And sort of, if you look at this, you can see that every point was identified, like what in the ground truth was 0 got identified with label number 3. What in the ground truth was 1 got identified with label number 2, and so on. The point here is that we want to group the data together, but which numbers assigned to this group of data points is completely meaningless. So it's important to know these all have the same label, these have all the same label, and these have all the same label. Whether that is 1, a million, or whatever, the algorithm has no knowledge about that because you didn't tell it anything what is 1 supposed to mean. You can later go in and say like, oh, I grouped all these users together, like let's look at the users, maybe there's interpretation for why these users got grouped together, and you can start to interpret it. But on itself, these indicator labels, these the 0, 1, and 2, they don't have any meaning. There's scores you can use that take this into account. For example, the adjusted rand score, which I'm not going to go into detail about, but basically it'll tell you whether your grouping of the data is a good grouping, not whether the labels are the same. And because we group the data perfectly, we get a perfect score of 1. So to make this, so for clustering to work, sort of, I mean, I showed you the data, and you said there's 3 groups, but this really makes assumptions about what are groups in the data, and it might not be obvious sort of what groups mean. So k-means comes with the assumptions that there are centers, and then there's like same size circles around these centers that make the clusters. I mean, it's the vertebrae diagram for people who know what that is. And so there are some data sets for which this doesn't work, like this one. So here, you might also say, oh, there's 3 groups in this data, and the group is this, this, and this. But because here, the distance in all dimensions is the same for k-means, so it can't produce elongated structures like this. So it'll fail to find these 3 clusters here. Maybe you also disagree that there's these are the 3 clusters. I don't know. But so k-means assumes that basically all the clusters have the same size in all directions. There's a lot of documentation about which clustering algorithm to pick. Some are listed here. So k-means is a very common one. Mean shift also doesn't work with a large number of points though, and also often not that well with high dimensions. dbScan works very well for large data sets. Affinity propagation is in there because there was a Nature paper. I have never seen it used and it doesn't work. The author is not here, I think. Spectral clustering doesn't work that well with large data sets, but it allows to have, it's much more flexible than k-means. Ward is also much more flexible and also works very well, scales well. And there's this plot that's from documentation. Let me zoom out for a bit. And it shows, like, for some data sets, what the different clustering algorithms do. So here the first one is k-means. And you can see that sort of for, why does it fail for the, okay, it's not supposed to fail for this one. Why does it fail for this one? Okay, but sort of if you have this circle on circle, because there's no, if you compute the centers of the circles, they're the same. So k-means will not be able to distinguish like the inner and the outer circle. Whereas algorithms like spectral clustering and maybe also dbScan and Ward with the right parameters will be able to distinguish them. Same goes for like this two bananas or half moons. Like algorithms like k-means will not be able to distinguish them, while other algorithms might. On the other hand, 2D toy data sets don't tell you much about actual data. So maybe don't interpret it too much into this. Only if you have a 2D toy data set, then you can. All right, so now I would like you to use the digits data set that we had before and cluster it using the k-means clustering algorithm. You know there's supposed to be 10 clusters, and then you can also plot the cluster centers. So k-means has this cluster centers attribute. So now these are 3 means in 2 dimensions. If you apply it to the digits data set, there will be in 64 dimensions. You can plot them as digits. If you're lazy, you can also load the solution. Okay, maybe I'm going to give you 5 minutes for that because we're kind of late. If you want, you can also compute the adjusted run score to see how well the clusters found actually overlap with the 2 digits.
In your first example with k-means, when you instantiated k-means, you gave it a random state. What's random in the object?
So the initialization, it's there's an iterative optimization algorithm, but it's in such a way that it will not find the optimum solution. It defines, because that is like NP-hard. So it'll start from some initial starting point, and the starting point is picked randomly. Actually, by default, it'll do 10 different starting points, run the whole algorithm for 10 different starting points, and give you the best of the 10 results. But still, there's randomness. It's actually, it implements a smart initialization strategy for k-means, which is called k-means++. So it runs 10 iterations of smart initialization by default. So there's randomness. For these 3 plops, it probably doesn't matter. Okay, maybe we'll go on. So just, I saw a lot of people that had a picture like this. I need to zoom in again. Can you see this in the back? Yeah? Thumbs up, thumbs down? Thumbs down? Oh. Like this? Better? Okay. So I saw a lot of images like this. This is the standard interpolation of imshow. So if you do imshow with one of the digits, it'll look like this. I mean, if you do how to pick a color map, not like this. Like this? Okay, never mind. Okay, give me a never mind. Okay. This is not a good color map for this. But also interpolation is not good because you want this image, which you can get by either doing interpolation to nearest or use match show. That's just an side note. Interpolation is probably not good for these images. Okay, but to the solution. So here, I mean, basically what it does is here it plots the cluster centers. Maybe how do you apply this? So we just instantiate k-means, set the clusters to 10, call fit predict on the data, and get the clusters. Then we have 10 clusters, each with 64 dimensions, because that's the number of input features. And then we can plot them here. We create the figure, and we put subplots in for each of the centers. And these are the 10 centers we found. And they look like they kind of identify digits. Actually, this one looks pretty good. No numbers there twice. I think it looks... I mean, this is a bit unclear what this is. So, which one is missing? 8. Okay. It also does like an additional thing where it uses isomap to project down in 2 dimensions and then colors them by the clusters. I don't really see anything in there. You can also do the adjusted rand score of digits at target and labels. I think it's called. It's called clusters. And okay, it's better than random guessing, but it's not that great. Okay, any questions?
Is there an analogous notion in unsupervised learning to like training and testing sets?
It depends. So it depends on what you want to do. If you are building a pre-processing system, like you want to do PCA, and then feed that to a classifier later on, build a new representation, you should split your data set, build a training data set, build a PCA only on a training data set. Because you'll have new data in the future that you want to generalize to. I mean, that's the main question. Do you want this to work for future data that you haven't seen yet? If you wanted to use it for future data that you haven't seen yet, use a train test split. The problem is here, though, that usually there's not a good way to evaluate unsupervised methods. So here, for example, for the clustering, I mean, I kind of evaluated it using this adjusted rand score, but for that I need the ground truth labeling. If I have ground truth labeling, why do I use clustering instead of classification? Usually if you do clustering, you don't have a ground truth labeling. And evaluating, is your clustering any good, most often consists of looking at the clusters. And do they make sense? The question, whether you want to try and test split or not, depends on, do you want this to work on new data that you haven't seen yet? If you use it for visualization, for example, you probably don't care. You have all your data. You want to look at it and see if there's structure in there. But also it's like, if you hollow the test set, what are you going to compute on this? It's often unclear how to give a quantitative estimate of how good the unsupervised model is. Like supervised models are much more straightforward in that sense. Okay. Any other question? Yeah.
So would it be fair to say that basically you're normally using unsupervised when you don't have the option?
Oh yeah. So yeah, I should have said that. So if you can formulate your task as a supervised learning task, do that. Only use unsupervised learning, like only do clustering if there's no option to get labels that are meaningful. I mean, Carl said getting labels is expensive. Actually, I think getting labels for spam emails is super cheap. You can just do it on mTurk. If you have something where you can hire like a cheap person to get you the actual correct labels, hire the cheap person. Sometimes, though, if you have like tumor detection or something, and you need like an expert, or you need or if you do something with astronomy, maybe you need a new satellite to get your labels, then maybe instead of doing that and spend a couple of billions, do unsupervised learning. But if you have the option to get cheap labels that are actually correct, you know this is the right thing to do, by all means, get the labels. It will always be much easier to evaluate, much easier to do. Okay, so now I want to quickly review. Actually, I'm not going to go through all of these things, but basically, I'm going to do my quick version is this. Everything has a fit. You use fit to build a model. And if it's a supervised algorithm, you give it an x and a y. If it's an unsupervised algorithm, you give it only an x. And you use the predict method if you want to get out a y, so a labeling, a target. So this is for classification, regression, and clustering. And you use the transform method for if you want to get out a new X, something that looks like data, something that has multiple columns, multiple features. So that's for preprocessing, dimensionality reduction, feature extraction, manifold learning, feature selection. And these are like the three methods that are most important. Fit, predict, transform. And score for supervised models. And that's really the meat of what you need to know for scikit-learn. And I think with this, goes over to Kyle. Or any questions? Nope? Okay.
Okay, so we have about an hour left before lunch. I guess we break at noon. I'm not entirely sure what the schedule says, but we have a big number of case studies and methods coming up. This is mostly like larger examples. We'll delve a little bit into digits still, but then we'll quickly move into larger data sets and hopefully a little bit more problems that seem applicable to you. This is going to be intense, and that's okay. That's why we have the notebooks. Once again, feel free to ask questions, comment, whatever. Ultimately, we want to make sure that these are good examples of scikit-learn towards the real world. Obviously, we're running MacBook Airs, not like big servers, so we're not going to be doing big data or anything resembling it. But we're going to be doing stuff that's hopefully interesting and hopefully gives you a better intuition of what we talked about all beforehand. So, with all that said, let me make sure I have the right one open. So we'll start off with classification of handwritten digits. So we've talked about digits a lot, because they're a very nice example. We can see that when we do unsupervised learning, they separate nicely into clusters, and we can visualize them well. We can plot cluster centers, and they mean something to us. That makes it a very nice example in general. So once again, we'll load the digits data set, do some matplotlib inline, matplotlib importing stuff, and we'll reuse some code that we showed a little bit earlier to plot the data set and look at what we're actually dealing with. It's really important, if you can visualize your input data, to visualize it, because here's where you discover things like corrupted files or like inverted indices or just random garbage that got into your data that can cause real problems. So it's really good to select some subset of your data and visualize it and try to find problems. So here we'll plot a subset of the digits, and we'll also put the labels on the axis. So you also have some nice examples of how to add text in matplotlib and this kind of stuff. Once again, we see that the digits are, because they're 8 by 8, they're kind of blurry and kind of hard to identify really well, but we can get the broad classes, kind of like we saw with the k-means. We can see the zeros, we can see the ones. Still, this is a little weird. But that's the nature of digits. If you look at real handwritten digits, you see problems like this.
So this brings up an interesting question here. So there are two pretty common ways that you'll see a 7, right? With the little across the middle or not. So, to us, obviously it's the same number, but I would imagine this might affect that as a.
So it really depends on your labels.
Question.
Yeah. Oh. Repeat the question, yes. So the question was, sevens, there's typically a couple different modes of drawing any digit. Like for a 7, you could just have the digit, or you could have the digit with a line through it. And it's easy to believe that either the labels could be wrong, or the classifier could maybe think that the 7 with a line through it is a 3. There's a chance for confusion there. So this is one of those things that, depending on who you are, you take two different approaches. There's one approach where you say, well, okay, I know that some 7s have a line through them, and maybe you give them their own label even. And you say, this is 7 with a line through it, and this is 7 without a line through it. And you kind of encode your knowledge about the way digits are written into the labels, or you have features that are basically like, is there a line or not? And then look at curvatures and all kinds of features based on that, instead of just looking at the raw pixels. You can also imagine that you don't want to do this, right? You know that the data itself tells you that 7s can or cannot have lines through them. So a good classifier should naturally learn, at least if it's trying to decide between 7s and 3s, that the presence of a line in the middle of the image shouldn't matter that much. And even zeros, we have this thing where you draw a 0 and you have kind of like a slash through it. So there's kind of a couple schools of thought on this. Some people would try to encode that information explicitly in your features. Other people might say, well, we'll learn it from the data. And so it really depends on how much data you have, right? It's easy to believe that if you have one example of every single digit and that's it, you're going to have to do some engineering of your features to generalize well. The counterpoint is if you have 1 million digits or 1 billion digits that are all well labeled, what do I care, right? So you kind of have two schools of thought on this, and I'm very much on the learn from the data side of things, and I'll be giving a talk Wednesday about that. But for now, we're kind of glossing over that and saying, well, okay, we know that even when we did the digits plot, we saw that like 3s and 7s, there might be some 3s and 7s that are closer together. It's very easy to believe that those could be the ones with lines through them. And if we have probabilistic interpretations, you could look at confidence and things like this. But ultimately, you can either encode it in your features explicitly, or you can expect to learn it from the data yourself. All right, so visualizing the data. Once again, dimensionality reduction using PCA. Here we use something called randomized PCA. It's basically the same thing, much, much faster for certain types of problems. If you look in the sklearn decomposition folder, there's a number of examples of different PCAs and different ways to use them that are useful for different problems. And a lot of the core devs for scikit-learn need different PCAs because they deal with big like fMRI data where there's massive amounts of features and things like this. So there's naturally kind of a little more focus on needing good PCA algorithms. So here we'll look at some of the principal components. Again, we see we got like a slightly different display here. Probably we need a random state here, if I had my guess, given that it is randomized PCA. So it's a little bit different. Not too special. We've seen this a lot before. We talked a little bit about linear versus nonlinear dimensionality reduction with the differences between isomap and PCA. We'll use it again. This is actually kind of a repeat of what we did before. But that's okay. It's always good to hammer it through. We ate snacks. Blood sugar's up. We got to get the memory going again. So we have isomap here. Separates things a little better. If you have a more recent version of scikit-learn, Andy showed t-SNE. That is kind of like the de facto, look how pretty my graphs are plotter these days. It does really kind of cool stuff to data, and then you have to ask yourself, is this really useful or not? It's kind of a tool that's explicitly for visualization. But it looks awesome, and put it in your presentations and show it to your boss. So we have all kinds of manifold applications. Given projections of the data, which numbers do you think a classifier might have trouble distinguishing? So here we can see pretty clearly, either for this example of PCA or for isomap, there's classes that are much easier to separate, at least in 2 dimensions, than others. So here we have what looks like probably 4 here. Then we have zeros kind of over here. Looks like these should be pretty obvious to separate here. Whereas 9s and 8s are kind of mixed up with 3s, which is very believable from our previous point about lines. If you think about the way a 3 is constructed, it's basically an 8 missing a little bit. So if someone's bad at drawing an 8, or if they do like a really skinny 8, it could look like a 1. Digits have a lot of weird problems to them. It was a request to talk a little bit about label noise. Digits are one of those examples where there will be label noise because there's different digits that are kind of ambiguous in the way they're labeled. So this is actually an important thing to think about. You have to think about, okay, well, I have these labels. How much noise is in my ground truth? What does that mean? Am I okay dealing with that? Or do I need to be robust to label noise? Or do I assume that my ground truth is truth? So these are all, it's kind of like the spectrum between unsupervised and supervised. There's some algorithms that are more robust to label noise and others that kind of fall apart. So, yeah. So the axes here are the first two components of isomap, if you will, and the same here, the first two components of PCA. So they don't, in PCA you can kind of assign meaning to the projection axes that you have. Like we plotted the first basis of digit PCA. It was kind of like 0-ish. But for isomap, it's not as clear what that is without plotting it. But typically with these methods, what you expect to see is like an ordering of the axes. So the 0th axis kind of encodes the most interesting stuff. Then the first encodes a little bit less, second, so on and so forth. No, the units aren't typically interpretable. Okay, so now we're on to a simple classifier called Gaussian naive Bayes. Won't go too into much detail about the math, but it's pretty simple, pretty fast, and pretty general. And it's been used for a long time. So once again, we import Gaussian naive Bayes, split the digits data. Let me move this line over here so people can see it a little better. Train the model, predict things. Question, why did we split the data into training and validation sets? I think we've hammered that point home pretty well. It's crucial for developing a real system that actually means something when you take it and use it to predict new data. So let's prod it again with the predicted labels to figure out how all classifications are actually working. And this is actually nice because we can visualize some of the errors of our classifier. And that is one way to figure out if my classifier is fooled by lines. Maybe I need to do something specific to handle that. So visualizing your errors is every bit as important as just printing the scores. And that's one of the things a confusion matrix gives you. You can see what things are easily confused and figure out if that's a label problem or a problem with the way you're encoding your data. So here we get a lot of stuff pretty right, which is exciting. This weird thing here got classified as an 8 or not classified as an 8, as the case may be. Yeah, I think it was not classified as an 8. It's not, they don't say what it was classified as, but it was not an 8. But, I mean, look at this 3. Really? Is that a 3? If I put that in front of you with no context, would you say that's a 3? I would not. I would say I don't even think that's a digit. I think that's something else. So, same thing here. A lot of the 3s in this data set are pretty wonky. So, once again, very important to visualize your data. See what's hard, see what's easy. So, one way we could use this information is if we think 3s are generally pretty muddy and pretty messed up on the pixel level, we could make another feature that explicitly handles 3s and extracts something interesting, some kind of curvature or some kind of different representation that helps classify 3s from everything else. So you can drive your classifier building and your feature engineering this way. And hopefully you'll see these errors go away and no new errors, and then you're doing better. And then at some point you'll introduce a feature that'll break other things, and then you get into the art of machine learning. It's not purely science. It's like art and science together. So we want quantitative measures of performance. We've seen this a lot. You can see our classifier is getting about 80%, which is not too bad considering the noise we're seeing on the data and given how easy it was to train this classifier, import naive Bayes, fit, predict. It's pretty straightforward. So we can look at the classification report, which has a whole bunch of different metrics. We'll talk about that a little later on. In general, these metrics kind of encode true positives and false positives and true negatives and false negatives. It's pretty easy to believe that for different tasks, you have different importances on this. Sometimes it's important to be right, and other times it's important to not be wrong. The pretty good example is medical tests. You're much, much, much better off telling someone, hey, you might be sick, come in for a secondary test, versus saying, oh, you're fine, and they're not. So for different domains, it's very important to think about, like, what is the price of being wrong versus the price of being right? If I'm wrong, do I lose a customer? That's a big deal. If I'm right, does that mean that people think I'm magical? Am I willing to trade false positives for true negatives? And there's a whole trade space with this. And we'll talk more about what these metrics mean and how to figure that out. So here we can also look at the confusion matrix. As Andy said, it's kind of like true labels here. No, true labels here, predicted here. So what you want to see is a nice diagonal. And that doesn't always happen, but it also shows you pretty clearly what things are messed up. So one way I like to visualize this a little, well, I didn't want to do that. Fine. So one way to visualize it is to look at the matplotlib display of this. So instead of classification report, we want confusion matrix. And we can also do matplotlib plots here. And it's a little easier to see. And I have metrics.confusion matrix. Yeah, so we see something like this. So it's just a visual representation of the matrix that we're printing, but it helps us a little more clearly see where the errors are. So if these are the true labels and these are the predicted, then we can see that for the true label of 1, sometimes we're predicting like 7. And that tells us something about the problems that we have either in our labels or in our classifier. So with that kind of simple case study out of the way, we'll move to an example with faces.
So if you want to skip 3.2, I don't think there's much in that.
Yeah, so I think we've pretty much covered most of what's in 3.2. I just want to show the face basis.
So not in 3.4.
Let's look here.
Okay. Sure.
Well, is it?
No, there's.
Yeah, so this is the face basis. I'll just show the face basis and we won't rehash PCA and showing bases and so forth. But it is interesting. We're going to be working with the LFW faces data set. If you have spare time, you can look at why it's good with PCA to recenter if you're going to do classification. We'll kind of breeze over that because we have an example of that earlier. So this is the kind of faces that we're looking at. It's similar to Olivetti faces, but a little different because it's famous people. And one thing you'll find if you operate on this data set a lot is George W. Bush just like dominates his data set for whatever reason. There's a lot of tagged pictures of him. And I think like Colin Powell's next and Ariel Sharon and like it's labeled faces in the wild. So someone kind of found pictures of celebrities or politicians because there's no copyright issues with their likeness and built a data set out of this. It's pretty nice to work with. It's large-ish and it gives you some nice intuitions about things. And you can also select how many faces from each person get into the data set and so forth. What we really care about is visualizing the mean face. So this is the mean face. This is the principal component, and you'll notice, well, it's actually the mean. So if you look here, you'll notice it has a little, whatever George Bushism is, that's what it looks like. So that doesn't necessarily mean that everybody's face, the mean, is George W. Bush. That means that for this data set, he is kind of like the dominant face, so he's going to dominate the mean. So this is another important point. When you want to look at statistics and say, oh, this means something, think very carefully about the meaning you're putting on the mean or the principal axis or whatever. It might not encode what you think it encodes. So here we can kind of see the shape of the components, and this is doing something called eigenfaces. It's a really famous face processing technique. Basically, if you visualize the principal axes of variance in different dimensions, like 0, 1, 2, kind of like Andy showed before, you see like a number of very kind of weird, scary, demonic faces, right? What this means is like these bases encode differences between different people to try to do the best job possible in separating the space in which the faces live. And that sounds really hand-wavy and weird, but what it means is there's variance in different dimensions and you need to encode that. And once again, you'll see like a few of them, encode like George Bushisms again. I don't know, he's a recognizable person, but whatever it is about that encodes his face. So it's obvious that if you have one of these, it's pretty useful later on if you want to do classification. And this axis is very active. That might be George Bush. So that's like a high indicator that you want to classify as him. And so that's one of the reasons that doing PCA beforehand can be useful. So
What's the intensity of the axis there?
Don't know. We're using IM-show, so it's probably normalized. That's the other thing. So if you're using IM-show does some nice stuff with images to kind of like make them look nice. But not only are the PCA axes typically not interpretable, you can try really hard, but typically I avoid it. IM-show is also normalizing things to show them to you. So things that look like very obvious in IM-show may not be obvious in the data itself. So sometimes you might want to swap between mat-show and IM-show to see what's going on. So I'll close a couple of these here. All right, so face recognition. This will be pretty fast because we've gone over the API. We know how to get classifiers. We've gone over why it's useful to use PCA beforehand for classification. We have the data set, and it's pretty straightforward. And you'll see that some of the examples kind of repeat a little bit. There's a reason for that. Different versions of these examples have existed in different places, and some of these are kind of supposed to be standalone. So in theory, you could take the 3.2 and 3.3 together and teach a little lecture about just PCA and eigenfaces. And if you have a meetup group wherever you're at, maybe that's a good example to show to other people if you do stuff with faces or images. So here we kind of see the count. Like I said, George Bush dominates pretty hard. Colin Powell is number 2, Ariel Sharon, Donald Rumsfeld, Gerhard Schroeder, who I actually don't know, but you can kind of get a count. And so it's important to think about this imbalance when you're doing classification, because that means de facto, if you default to predicting everything as George W. Bush, you might get a pretty good score. So you might say, oh, I'm scoring 0.8, I'm doing really well, right? But if George W. Bush is 80% of your data, you're basically just predicting the most common label, and that's not very useful. So it's also important to look at these statistics when you're analyzing a classifier to figure out how it's working. So this talks a little bit about how the pre-processing outside of scikit-learn was done. If you do lots of image processing, you've probably heard of OpenCV, and if you haven't, you probably will. It has a lot of built-in kind of the classic image processing stuff. We also have Scikit Image. There's actually a tutorial going on now on that, and they have some of, but not all of, the same stuff as OpenCV, and they take a slightly different approach. But a combination of OpenCV and Scikit image can get you a long way with most image processing tasks. So we want to do support vector classification of the images. We won't talk too much about what support vector classification is. You can think of it a lot like the logistic regression we talked about before. And later on in the afternoon, Andy will have some really cool notebooks that go in depth on SVMs and have some cool widgets that you can play with, and it's really nice. So here we get the data, we train test split again. Now we want to do pre-processing with PCA. So this is kind of the first step to building what we call a machine learning pipeline. And we'll talk a lot more about pipelines once again in the afternoon, but basically it means we have a series of steps we want to perform on the way to classification. And normally you want to be very careful about this, and you want to put only training data through the pipeline to train, and then put only testing data through the pipeline to predict. There are people who say, oh, it's unsupervised, they can train on the test data. I am not a fan of that, and I think you're asking for a lot of trouble when you do that. It's much easier to simulate this system, got all new data, just run it. So with that, we use randomized PCA to get the bases of the different faces, and then we'll take the data set and we'll project the large dimensional raw pixels onto each basis that is some weird demonic face. And that's one type of feature extraction. You could actually imagine, if you had a lot of free time on your hands, drawing the George Bush template of his face and then having that as a basis, an Ariel Sharon basis, and having that for his face. But we learned that naturally from the data. So here we want to do a classification. We have some hyperparameters here that we set and select. We'll talk a little bit about hyperparameter selection later. There's a lot of kind of subtle details to that. But for now, a lot of times the defaults for SVM will just work. And same with logistic regression. They're pretty robust to most settings of the hyperparameters. So let's visualize some of this. Yeah, so we can see the ones we got right and the ones we got wrong. So we're doing more than just predicting George W. Bush for everything, so that's good. We're getting some mix-ups between different ones, and it's not clear why that is. It's a little hard to inspect and figure out exactly why one image is wrong and one image is right when you don't have explicit features. We use PCA to do feature extraction, so it's a little hard to figure out what's going on. Probably a random seed again, if I had my guess. So if we look here, so here there's also not a random seed. Here there's probably not a random seed. Oh, so there is a random seed here. There's not one here. So let's see if we get something different. So usually when these kinds of things happen, somewhere there is a random seed that has not been set. So this once again points to the importance of always using the random seed for deterministic running of scripts and so forth. And so we'll try to go back and find that and clean it up. And it could also be in the fetcher itself. So okay, given that classifier, yeah.
So is that just something that's important when in a situation like this where you want someone to be able to compare results, or do you actually use that in?
So it's important. I would say it's important in production, so you have guarantees about what's happening. You can use random seeds and just use them randomly and say, well, in production we'll get something that should work fine. But that means that you need to train and run the classifier with a whole bunch of different random seeds to figure out how it's doing and how it performs, and the statistics of what's the worst I did and what's the best I did over 10 runs with different random seeds. And you actually run into a very large problem of the random seed is also a hyperparameter. And I won't harp on it too much, but when we talk about cross-validation, the random seed can actually matter. Like a really bad choice of random seed for the iris data could slice all zeros and ones and leave the twos as test data if you're really unlucky. So there's kind of a trade space of like you want things to be deterministic, but if you choose that seed wrong, you might pull your hair out trying to figure out what the heck is going on in my classifier when really it's switch 1999 to 2000 or 0 or whatever, and then things are fine.
So in my intuition, it seems like if you're really getting different results based on the random seed, then you're unlikely to work on the real world data, but I don't know if my intuition is correct.
So the statement was if the intuition is if your random seed matters a lot, you're unlikely to generalize to the real world. And that's right in a sense. It really depends on what the deviation is. Obviously, if you switch the random seed and it goes to 0 from 80%, that means you're very, very, very susceptible to randomness. You're very susceptible to what data you see and what order you see it in. But at the same time, that doesn't necessarily mean that it is a problem with the classifier. It could be something fundamental to your data, like if it's very imbalanced and you missed that very small number of labels, then that could be it. There's any one of a number of things.
So if you have a big enough data set.
So the comment was, if you have a big enough data set, the random seed matters less. And I would say yes, given that larger data set has equal numbers of labels. If your data set gets larger with only one particular label, you don't really gain anything. And typically, if we get into something called ensembling, you can actually use this different randomness to your advantage. And when we talk about random trees, we'll see it more. So there's ways to exploit the fact that different random seeds give you slightly different outputs, and you can use that to make a better classifier that's more robust. So here we have a classification report, and it's even got the names of the people, which helps for visual inspection. We'll talk about metrics a little more later. Confusion matrix, again, shows us which predictions we're getting wrong, so that can be helpful if we have manually extracted features or if we think there's noise in like the labeler. Someone who labeled the data couldn't distinguish Rumsfeld from George Bush. That might tell you something about the data you need to go clean up. And here we look at the F1 score, which is just a stronger method of comparing true and false positives and all of these things. We're kind of introducing pipelines a little early. I mentioned earlier that you can use a pipeline. You can think of it as a pipeline, and scikit-learn actually gives you a pipeline object that explicitly says this is the pipeline of what I'm training. And we'll talk about that more, I think, in the afternoon. But what you should see if all the random states and stuff are set correctly, you should see basically the same results as before. That's all a pipeline is. It's a helper. So final note, we use eigenfaces. There's a paper on it, pretty famous. If you're interested in the math behind it, you can take a look at that. So now I will turn it back over to Andy for text and SMS.
All right, so now we'll talk about how to work with text data. So that is a very common type of data, so this will be like kind of a new thing. Or maybe the last new thing this morning. So sorry, I'm fighting a little bit with the Mac and the zooming out part. Command plus and command. Okay, so basically, scikit-learn works with these matrices, number of samples times number of features. And there's a fixed number of features, and this one feature is like a column. It means the same for every sample. And if you have some text, like you have news articles or tweets or emails, they have variable length, and sort of which word you are doesn't really have that much meaning. So it's like having these variable length text is very different from having this number of samples times number of features matrix that we want. And so there's the back of word method, which is a very common method to go from text to a representation that we can use with scikit-learn. And it's very simple. So first, you start with a string. We assume that each sample is one string. So it could be just one sentence, could be one tweet, could be one news article, could be one book. Like if you want to say, like, want to classify which author is, who's the author of this book or something. So let's say our string is, this is how you get ants. The first thing you do with the example is you tokenize it, which is basically breaking it up into parts. There's very simple methods to do this in scikit-learn. There's much more advanced methods in things like NLTK. What we do basically is we use a regular expression to split on white spaces. So we get the words, and then we lowercase everything to like normalize it a little bit. So we don't care if something's at the beginning of a sentence or something like that. You could also do things, if you wanted, you could do things like spell correction or removing the S from a plural or things. But okay, so we went from a string to a series of these tokens, which are kind of normalized words. Then we build a vocabulary over all the words that appear in our training data set. So let's say over all the emails that we collected, or over all the news articles, over all the books we want to classify. And so there will be a lot of words. It will probably not be all of the English language, but it will be like at least in the tens of thousands, hundreds of thousands. And then we count, so this is sort of the vocabulary here, from artwork to disk. And then we will count for each word how often, or for each token, how often does it appear in this string that we started with. So we started with this string, this is the data point we want to encode. And so for the word ants, we have a count of 1. For the word get, we have a 1. For the word how, we have 1. For the word is, we get a 1, and so on. And for all the others, we have 0. And so this is where sparse matrices come in. Kyle alluded to that previously. So we don't want to store all these zeros. We only want to store the ones. So we'll store that there's a 1 here for ants and get and you, and so on. So let's see how this works. This is implemented in the count vectorizer in scikit-learn in the feature extraction.txt module. So let's say we have 2 strings here. Some say the world will end in fire, some say in ice. I hope I don't get into copyright issues here. So there's 2 samples, length of 2. This is not a matrix. This is not number samples times number features. This is just a list of 2 strings. And now I can put this in the count vectorizer. I can call fit as always. So count vectorizer is kind of unsupervised feature extraction. What this did was it built a vocabulary. And this is a dictionary. Here, you can also get this by doing get feature names. So this maps words to like indices in the feature vector. So here, there's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, yeah. Maybe I didn't need to count that. There's 9 words in this that appear in the whole data set. So much less than 100,000 you'll usually have. And so if you now use the transform method, we get a representation that is 2 times 9, 2 samples because we have 2 strings, and 9 is the number of features here because there's 9 words. And this is a SciPy sparse matrix. There's 12 stored elements because there's only 12 non-zeros. And here, this is the feature matrix, what it looks like. So the first string contains all the words. Maybe I'll print the... Oh, I'm sorry. You should have reminded me to become larger again. Okay, sorry. So X was this, and so all the words apart from ice appears in the first one. So get feature names also gets you the name. So this is and, fire, ice, in, say, they're sorted. So all words but fire appear in the first one, and the second one only has ice, say, in, no, this is ice, in, say, some. Okay. And you can also do an inverse transform, and it'll give you just from these indices which words appeared in the. So it'll do the back translation that I just did manually. So this is called bag of words because you lose the order of the words. So you just count how often something appears, but you don't care about the word order at all. There's a thing called okay, so this is like the most simple and one of the most common ways to encode text data. Maybe any questions about that? Okay. So there's a thing called TF-IDF, which is a method to rescale these counts that often works well for classification tasks. And it stands for term frequency and inverse document frequency. And it does basically two things. It normalizes each vector itself so that longer things are not more important. So if you have a very long text, it will be normalized so that it's treated similar to a shorter text. And also make things more important that are rare. So something is very often in a document, but very often in every document, like which you might have removed as a subword. But let's say you didn't do that. So the appears very often, but it's not really important because it will appear in all your documents. So where something that is very specific to a particular document, like a particular email or tweet, you want this to be more important, and that's what TF-IDF does. So again, I instantiate it here. I call fit on our 2 lines of fire and ice, and then we can plot it. So I print it here. So this is the transformed version. You see there's no zeros and ones anymore. There's no counts, but it was renormalized. So there's now here 4 unique numbers, and basically in the first one, the things that are unique to the first string, these are fire and a couple of others. The ones that are unique are 0.09, 0.39. The ones that appear in both are 0.28. Because they appear in both, they have less weight. For the other one, there's also the one that appear in both have 0.45. The one that appears only in this one has 0.63. And here, each of them has more weight because it's a shorter one. It's a shorter string. And it's often good to just try this one out. Sometimes it will give you a boost in performance when doing text classification. So, as I said, bag of word completely removes all the order in input. Doing TF-IDF just rescales it, but also gets rid of all the order. There's a way to encode order, though, in a very simple way, which is don't look at single tokens, but look at pairs of tokens that appear after another. That is called using bigrams, or more generally n-grams, using n tokens that appear after each other. And you can control this in scikit-learn using the n-gram range, which says what is the minimum number of tokens I want to consider and what's the maximum number. So doing 2, 2 means look only at pairs of tokens. If I call fit here on x, I get all pairs of tokens that appear one after the other. So I get and in ice, and fire, say in, and so on. And often this order is important because you can imagine if you have not before something, it completely inverts the meaning of the word. So if you want to say, like, are these positive or negative customer reviews, if it says not good, it's very different from saying good. Okay. And again, you get here you can do this with TF-IDF vectorizer or count vectorizer and get zeros and ones. If you want to have not only pairs, but you want to have single words and pairs, you can do n-gram range 1, 2, and then you'll get the singles and the pairs. And the higher you go, the more features you'll get. Okay. Another thing that you can do is not look at words or at tokens, but look at characters. So sometimes you only have a single word and you want to classify that word. Or one example I worked with recently is is you have last names of people and you want to classify what is their ethnicity. But you can also think of like you want to classify, is this a named entity? So is this a person, or is this just a noun? Or is this a name of a place or something like that? And so the default is using analyzer equal to word, which does this separating words into tokens by white space. If you do analyzer equal to char, it will look at character levels. Usually it doesn't make sense to do 1 grams on character levels. Then if you do n-grams on character levels, it means it will count how many A's there are and how many B's. That's usually not very important, not very informative. But if you look at 2-letter pairs, you get something like this. So here actually there's white space and E, white space and F, and so on. So here you have word endings and word beginnings. If you use more of these, you'll get longer and longer chunks of the sentence. It's actually often helpful if there's a lot of misspellings or something, or if there's like weird spellings, that might help. Okay. Any questions so far? Yeah?
So you mentioned NLTK briefly earlier. Is there any rule of thumb for when you would want to tokenize with NLTK versus this?
Okay, the question was when would I use NLTK for tokenization versus when I'll do this. So basically, for classification, I would probably use the scikit-learn ones, and so it's easier to start out with using the scikit-learn one and see how that works. And then if you want to do more advanced stemming, you can give it a different analyzer here or tokenizer. So there's a tokenizer option here, and that will probably be faster than using actually the vectorization from NLTK, but you can give a tokenizer and use like a Porter stemmer or something like that, and do that. It'll probably make your results better. But I think the classifiers are like faster and more robust than scikit-learn, probably. So for the machine learning part, I would use scikit-learn, and the count vectorizer I think is also faster. But so I would just start with that. And then add more advanced preprocessing using NLTK and see if that helps. All right. So now, what time? We got 15 minutes. So I want to do an example of how to do this. Text classification using scikit-learn. And this is very simple classification task, basically text classification for SMS spam detection. This is like an open data set to classify text as SMS spam or not SMS spam. So there's just this data set file is a text file, and it starts with ham. So sorry, this line might not work on Windows. I was too lazy to make it work on Windows. So this just gives you the start of the file, of this text file here. Each line is either ham or spam, then a tab, and then some string. And we want to read this into Python. You could use pandas for this, which would probably be the best way to do it, but I didn't want to depend on pandas for this tutorial. Go ahead, use pandas if you like. Here I basically just used open, iterated over the lines, and split it on the tab, got the text out, and checked if the first entry was ham. So it's 1 if it's ham and 0 if it's not. Okay, just reading a text file. So now text is a list of strings. This is a British data set, as you might notice. And I replaced all the pound signs with dollar signs because otherwise there's UTF encoding troubles. Okay, and so Y is either true for ham or false for spam. Yeah, so, and both are lists now. Then we do train test split. Maybe do a random state here. And now we have some text training data and labels and test data and test labels. We use the count vectorizer, instantiate it, fit it on the training data, so the text. Then we get a vectorized form of the training and the test data. We can look at the size of the vocabulary. This is a rather small data set. Did I print how long it is? I did not. Sorry. So these are only like, in total, I think like 6,000 samples. So it's a pretty small data set. And so there's only 7,400 words. So this is like, if you, on larger data sets, it will be much larger. And you can see what the features here are. They're sorted. Often they're numbers. So the first ones are usually numbers, not very interesting. If you look at the middle, you'll get something like this. Yeah. So training and test both have 7,464 features. It's the number of unique words that appear, and these are number of training and test data points. Now we are in a regime where, with the count vectorizer, we went to from text to sparse matrix. So now we can use all of the scikit-learn machinery. We'll use a simple. Yeah. Kyle, can you make a note of that? Anyhow, we'll use a logistic regression, not a multinomial naive Bayes, because I like logistic regression better. So now we can just call classifier.fit with the sparse matrix, the training labels, and then score on a test set. And we get 98% correct. Okay, so this is a pretty simple task. And we can also look at the score on the training data set. It's basically near perfect. So this linear model, which is kind of a very simple model, it finds this line or hyperplane, basically can do perfect on a training data set and near perfect on a test data set. However, this is like now very black boxy. You have no idea what this actually did. Linear models are kind of nice to inspect because they're simple. For other models, it's harder to understand what they're doing. But for this one, yeah, we actually can see what they're doing. I wrote this function called visualize coefficients. So the linear models learn a weight for each feature that says, if this is present, if this word is present, how much should it be one class or the other? And this is just getting the largest coefficients. So we have, for each word, we have a coefficient. So we have 7,464 coefficients. And I get out the 25 largest and smallest. And then I get so that's what I do here. I sort it, get 25 smallest, 25 largest. And so these interesting coefficients are the indices of the coefficients. Then I plot them and label them with the feature names. And you can see here, I hate the non-presence of scrolling. You can see that if there's text or ringtone or one or claim in the SMS, it's probably going to be spam. Makes sense. And then there's like different things that say that it's not spam. Maybe I can. It's command. Yeah, it's command. So my, me, sorry, and so on are a sign that something is not spam. Okay. Then we can play around a little bit with the feature extraction if we like. For example, there's some things in here like 84484 that don't seem to be like an important feature. So the classifier learned that this seems to be important. there's an option called MinDef, which means minimum document frequency to include a word. So we want a word to be at least in 2 documents to be included. And that gets rid of a lot of noise and is often helpful for small data sets. And there's not a big difference in, I mean, it's slightly better, I think, at least with the last random state I used. But if you look at the coefficients now, the words probably make much more sense. Okay. So this is here a slide an overview of the pipeline in general. It's very similar to what we did with the faces. So we do a fit transform of the data set. We get feature vectors out. We learn a classifier. We transform our test data set, apply the model, and then compare to the expected labels. Wait, what time is it? Okay, we got 10 minutes. So now I would like you to try the same with TF-ID vectorizer instead of count vectorizer. Visualize the results, and also maybe play with the n-gram range and see what happens. Yeah, and in 5 minutes, I'll show you some solution, and then we break at 12. And we'll be back at 1 o'clock for the second part. All right. Yeah. Okay. Questions?
Question, what if the train corpus doesn't contain the word that later appears in another of the that you're trying to classify?
So the question is, what if a word appears in the test data but not in the training data set? And so basically, the reason... Okay. So it'll be ignored is the short answer. The thing is that if it doesn't appear in a training data set, your classifier will not be able to learn anything about it because it never saw this word. So it doesn't know, does this word mean it belongs to spam or to ham, so it doesn't really make sense, and the model doesn't even know that this word exists. So for that reason, you create your vocabulary only on the training data set. So everything that is not in the vocabulary will be ignored. Any other questions?
So some ways with the classifier report if something is completely different from the training examples, kind of like in the example we had with the digits, there was some digit that even a human being couldn't recognize. You just have it reported instead of being labeled as one of the classes. Kind of introduce a new class, unknown or something.
Okay, so the question was, I repeat the questions for the recording, by the way. So the question was, what if there's something entirely new in the data that was not in the training data? And can we just maybe say, there's something weird happening here, instead of making a prediction that's probably not very helpful? And so there's multiple ways to work with that. One is, instead of making hard predictions with predict, most classifiers in scikit-learn have something called decision function or predict proba, which gives you an uncertainty estimate. And you can make predictions for something only when you're very certain, and when you're not as certain, you'll give it a different label, or you just decide not to make a prediction. The other way would be to maybe pre-process it with an outlier detection method that tells you, these data points don't look like my data. That is not specific to classification, but you could just do this beforehand. Yeah, I probably would go with it depends a little bit on this cost of making false prediction that Kyle talked about. So yeah, depending on what this cost is, you might want to reject something and not make a decision. All right, it's nearly time for the break. So I just want to give very briefly some results that I found interesting. Actually, someone found out if you only look at character levels, you can even do better on this data set. which means it's a very silly data set. So something spam if there's a dollar sign in it or something like that. Maybe I'll use a better one next time. But one thing that I found interesting is if you do n-gram range, that's 1, 2. So look at 1 grams and 2 grams. You get somewhat better. And the main reason is, so most of these, the important ones are still 1 grams. But here, you can see that your call was picked up. So if something has call in it, it's probably spam. But the phrase your call doesn't happen in spam. So here, looking at these 2 grams is really important because this phrase is characteristic of spam unless it's your call. Yeah. All right. So that's all I wanted to show here. Now off for breakfast, lunch, and I'll see you after the break.
Can we leave our stuff here?
Yes, I think you can leave your stuff here. It should be fine. I will do that. Feel free to grab me during lunch.